What did it mean for a world to be young? Does a planet remember the sky it was born under? Tonight, we journey to a time so deep, it feels like a dream. A time before the planets we know existed as they are today. We are drifting back nearly 4 billion years, to a moment when the solar system was still a chaotic and beautiful work in progress. There is nothing to do now, nothing to solve. We will simply wander through this ancient question together. But first, allow yourself to settle in. Find a position that feels comfortable and restful. Notice the gentle weight of your body, the soft fabric against your skin, and become aware of your breath, a quiet, steady rhythm, in and out. Before we begin our journey into the distant past, I wonder where you are settling in from tonight. If you feel inclined, you might share your city or town, and the time of your evening, in the space for comments below. It is a quiet way of connecting us all as we prepare to drift through the cosmos. Our journey begins not with a single world, but with the space that surrounded them all. We are entering a period that geologists of the future will call the Hadean Eon, a name that evokes a fiery and formidable beginning for our Earth. But tonight, we will see it not as a place of chaos, but as one of profound and serene creation. Imagine yourself suspended in the quiet darkness of space, nearly 4 billion years ago. The planets are not the familiar steady points of light we see in our own night sky. They are young worlds, still warm from their formation, their orbits still finding a permanent harmony. The space between them is not empty. It is filled with a fine dust, the last remnants of the great cloud of gas and dust that birthed the sun and all its children. This cosmic haze catches the light of the young sun, creating a faint ethereal glow throughout the solar system. This is a time of immense and beautiful transition. The initial fiery process of planetary formation, of small bodies colliding and merging into larger and larger worlds, has mostly ended. The planets have gathered nearly all the material in their paths and have settled into their spherical shapes, but the solar system is not yet truly peaceful. The final act of its creation is about to begin. A grand and sweeping event that will leave its mark on every single world we are about to visit. Think of this moment as the quiet before a cosmic rain, a slow, patient, and transformative shower that will last for millions of years. It is from this shared experience, this final system-wide storm, that each planet will emerge with a unique story, a unique character, and a unique destiny, all waiting to unfold in the vast quiet of the eons to come. Let us now gently submerge ourselves deeper into this ancient time. The name Hadean comes from the Greek word for the underworld, Hades, and it was chosen by geologists to describe a time in Earth's history that was thought to be hellishly hot, with a molten surface constantly bombarded from above. It is a dramatic name, born from our human perspective of what is hospitable and what is not. But for our journey tonight, we can set aside these ideas of harshness and instead see this era for what it was, a necessary and peaceful stage of cosmic becoming. The solar system, in this moment, is like a great workshop where the final touches are being put on a masterpiece. The heavy work of construction is over, and now comes the delicate, finishing work of sculpting and shaping. 3.8 billion years ago, the planets we know were in orbits different from their present ones. The giant worlds Jupiter, Saturn, Uranus, and Neptune were likely gathered in a much more compact arrangement, closer to the sun and closer to each other. Beyond them lay a vast, dense ring of countless icy bodies, a primordial reservoir of comets and dwarf planets, far more massive than the Kuiper Belt we know today. This arrangement was not destined to last. The giant planets, in their slow dance around the sun, were exchanging gravitational energy with this outer disk of icy worlds. This interaction, this gentle but persistent cosmic conversation, was causing the orbits of the giants to slowly shift. Uranus and Neptune were drifting outward, while Jupiter and Saturn were moving in their own celestial rhythm. It was a process that unfolded over hundreds of millions of years, a change so slow it would be undetectable to any observer in a single lifetime. But in the patient timescale of the cosmos, this gradual shift was leading to a moment of profound transformation. The orbits of the two largest planets, Jupiter and Saturn, were slowly approaching a special relationship a point of powerful resonance where Jupiter would complete 2 orbits for every 1 orbit of Saturn. As they neared this alignment, their combined gravitational influence on the solar system began to grow, like a musical note swelling in intensity. This growing resonance sent waves of gravitational energy through the entire system, disrupting the stable orbits of the other giant planets and, most importantly, stirring the vast, dense disk of icy bodies that lay beyond them. The calm of the outer solar system was gently but irrevocably broken. And with that, the stage was set for a final, beautiful reign of creation that would reshape every world from the innermost to the outermost. This was not a violent catastrophe, but a necessary gravitational rebalancing, a slow, majestic settling of the entire solar system into its final, too stable form. It is this moment of quiet transition that serves as the backdrop for our entire journey tonight. This gravitational rebalancing of the giant planets gave birth to the defining event of this era, an event that future astronomers would name the Late Heavy Bombardment. It is a name that suggests violence and destruction, but let us instead imagine it as a slow, cosmic storm, a delivery system that brought the final building blocks to the newly formed worlds. As the orbits of Uranus and Neptune shifted outward, they ploughed into the dense primordial disk of icy planetesimals. Their immense gravity acted like a shepherd's hand, flinging these small, icy bodies in all directions. Billions of them were cast out of the solar system entirely, sent on lonely journeys into interstellar space. But billions of others were sent tumbling inward, their paths now set on a long, graceful fall toward the sun. Simultaneously, the powerful resonance between Jupiter and Saturn sent gravitational waves sweeping through the asteroid belt, the region between Mars and Jupiter where countless rocky bodies orbited. These waves stirred the asteroids from their stable paths, sending a second, distinct population of rocky impactors hurtling into the inner solar system. And so, for a period lasting perhaps 200 million years, the entire solar system was filled with this silent, steady rain of both rock and ice. It was not a constant, crowded barrage like a meteor shower. Rather, it was a slow and patient process. Centuries might pass between major impacts on any given world. But on the vast timescale of geology, it was a period of intense and constant reshaping. Every planet, every moon, without exception, was touched by this storm. The surfaces of the inner rocky worlds were sculpted by countless impacts, each one leaving a circular scar, a crater that would serve as a permanent record of this time. The surfaces we see today on the Moon and Mercury are, in essence, preserved landscapes from the end of this great cosmic storm. On worlds with atmospheres, like the young Earth, Venus and Mars, each impact was a dramatic but fleeting event. An object would silently streak through the sky, its arrival marked by a brilliant flash of light that would momentarily outshine the sun. The impact would send tremors through the planet's crust and launch vast plumes of vaporized rock and dust into the atmosphere. But this storm was not just about sculpting surfaces. It was also a delivery service of profound importance. The comets arriving from the outer solar system were rich in water ice. As they impacted the inner planets, they delivered vast quantities of water, replenishing the worlds that were close to the sun, and potentially creating the first oceans on worlds that had formed dry. Alongside the water, these comets and some asteroids also carried complex organic molecules, the very chemical building blocks of life. So, as this great storm rained down upon the inner worlds, it was delivering not just rock and ice, but also the potential for life itself. It was a creative process disguised as a destructive one, a final, generous gift from the outer solar system to its smaller, rocky siblings, preparing them for the billions of years of quiet evolution that lay ahead. Let us now turn our gentle attention to the messengers of this ancient time, the asteroids and comets themselves. These were not simply random rocks. They were time capsules, pristine remnants from the very dawn of the solar system, each carrying a story about the region where it was born. The impactors came from 2 distinct populations, each with its own character and its own gifts to bestow upon the planets. First, there were the asteroids, which originated primarily from the belt between Mars and Jupiter. These bodies were the leftover building blocks of a rocky planet that never managed to form, its growth constantly disrupted by the immense gravity of nearby Jupiter. These asteroids were primarily made of silicate rock and metals, much like the material that formed the inner planets themselves. Some were dense and metallic, the shattered cores of larger bodies that had differentiated and then been broken apart by ancient collisions. Others were stony, composed of the same minerals we find in the crusts and mantles of Earth and its neighbors. When these rocky impactors struck a planet, they added to its mass, but they did not fundamentally change its composition. They were simply returning home, rejoining the same family of materials from which they were born. Their impacts were powerful, shaping events, leaving behind vast craters and triggering volcanic activity, but they were delivering more of the same rocky ingredients. The second population of impactors, however, was far different and in many ways far more transformative. These were the comets, hailing from the cold, dark depths of the solar system beyond the orbit of Neptune. These were not rocks, but delicate aggregates of water, ice, frozen gases like carbon dioxide, methane and ammonia, and dust, all loosely held together. They were often described as dirty snowballs, and they were relics from the coldest part of the solar nebula, where volatile compounds could freeze solid. Mixed in with this ice and dust were complex carbon-based molecules, the organic chemistry that forms the basis of all life as we know it. These molecules were forged in the interstellar cloud that predated our solar system and were preserved in the deep freeze of the outer reaches. When one of these icy comets plunged into the inner solar system and struck a planet like the Hadean Earth, the impact was profoundly different from that of a rocky asteroid. The immense energy of the collision would instantly vaporize the comet's ice, releasing enormous clouds of water vapor into the planet's atmosphere. Over millions of years, this steady delivery of cometary water is believed to have played a crucial role in forming or supplementing the oceans on Earth, Venus and Mars. And with the water came the precious cargo of organic molecules. These compounds, delivered by the billions, would dissolve in the new oceans, creating a warm, chemical-rich environment, a primordial soup of possibility. The great cosmic storm was therefore a dual process. The asteroids were the sculptors, carving the surfaces of the planets, while the comets were the gardeners, delivering the water and seeds from which something entirely new might eventually grow. Let us now imagine what it might have been like to stand on the surface of any young planet during this time and gaze up at the sky. It would have been a sight far more dynamic and alive than the calm, predictable sky we know today. The air itself would have been different. On a world like the early Earth, the atmosphere was dense and hazy, likely tinged with a reddish or orange hue from methane and other compounds, and it was completely devoid of oxygen. The sun would have appeared as a softer, less brilliant disk, shining through this thick atmospheric veil. But the true spectacle would have been the constant celestial motion. The space between the planets was still filled with a significant amount of dust and small debris, the last vestiges of the protoplanetary disk. This dust would have scattered the sunlight, creating a perpetual, faint twilight glow across the sky, a phenomenon known as the zodiacal light, but far brighter and more prominent than the subtle version we can sometimes see today. The night would never have been truly, deeply black. Against this luminous backdrop, the sky would have been filled with silent, fleeting streaks of light. Meteors, or shooting stars, would have been an incredibly common sight, not a rare treat. As the Earth plowed through the dusty debris of the solar system, countless small particles would burn up in the upper atmosphere every hour, creating a steady, silent firework display. And then there were the larger visitors. Comets, on their long journey in from the cold outer darkness, would have been a constant feature of the sky. One could imagine several being visible at any given time, each a soft, fuzzy patch of light with a long, ethereal tail of dust and gas stretching away from the sun. These tails, pushed by the solar wind, would have painted the sky with delicate, shifting brushstrokes of pale light. They would grow brighter as they approached the sun, and then slowly fade as they retreated back into the deep, a silent, majestic procession of icy wanderers. The most dramatic events would have been the impacts themselves. A larger asteroid or comet, one destined to strike the planet, would first appear as a new, bright star in the sky, growing steadily in brilliance night after night. As it drew closer, it would resolve from a point of light into a visible shape, a small dark body hurtling through space. Its final moments would be a silent, impossibly bright streak across the sky, a flash of light so intense it would cast sharp shadows across the landscape, momentarily turning night into day. There would be no sound to accompany this flash, as the object would be moving many times faster than the speed of sound. The ground-shaking tremors would only arrive minutes or even hours later, a deep, resonant rumble traveling through the planet's crust. This sky, filled with constant motion, with the gentle glow of cosmic dust, the silent dance of comets, and the brilliant flashes of impacts, was the shared experience of every young world. It was a sky that spoke of a solar system still in its final act of formation, a place of serene but profound and ongoing creation. Like any storm, the late heavy bombardment could not last forever. It was a process with a natural conclusion, a final, fading echo of the solar system's chaotic birth. The storm was fueled by a finite number of asteroids and comets, a vast but limited reservoir of material that was being steadily depleted. The gravitational dance of the giant planets that had initiated the storm was also, itself, the mechanism that brought it to a close. The main engine of the bombardment was the gravitational influence of Jupiter. As the king of planets, its immense gravity acted as the solar system's great gatekeeper. Many of the comets and asteroids that were sent tumbling into the inner solar system were not destined to strike a planet. Instead, their paths would eventually take them close to Jupiter. When a small body passed near this colossal world, Jupiter's gravity would act like a powerful slingshot. Most of these objects were unceremoniously ejected from the solar system altogether, flung out into the vast emptiness of interstellar space on paths that would never return. With each pass, Jupiter was methodically and patiently clearing the solar system of its remaining debris, one icy comet and rocky asteroid at a time. At the same time, the orbits of the giant planets themselves were beginning to settle. The great migration of Uranus and Neptune into the outer disk of planetesimals was reaching its end as they swept up or ejected most of the material in their path. Jupiter and Saturn, having passed through their powerful resonance, were now drifting into their final, stable orbits, the same orbits they occupy today. As the planets settled, the gravitational disturbances that had stirred up the asteroid belt and the outer disk began to subside. The source of the storm was quieting down, and so, over the course of about 200 million years, the frequency of impacts began to decline, slowly at first, and then more rapidly. The sky began to clear. The constant rain of meteors lessened, the procession of comets thinned, and the cataclysmic, world-altering impacts became rarer and rarer events. The cosmic dust that had filled the space between the planets was gradually swept up or blown away by the solar wind. The faint, perpetual twilight faded, and the nights became darker, deeper, and more peaceful. The solar system was transitioning from its turbulent adolescence into a long and stable adulthood. This fading of the great storm marks a pivotal moment in our story. It is the end of the era of formation and the beginning of the era of evolution. With the skies now quiet, each planet, bearing the scars and the gifts of the bombardment, was now free to begin its own unique, the solitary journey through the next 4 billion years of cosmic time. And it is to these individual journeys that we now turn our attention, beginning at the very heart of this newly settled system. At the center of our newly settled solar system, the young sun anchors everything in its immense gravitational embrace. It is the heart of the system, the source of light and energy that will dictate the fate of every world. But the sun of 3.8 billion years ago was a different star from the steady, familiar presence we know today. It was a star in its youth, with all the temperament and volatility that implies. To understand the planets of this era, we must first understand the star they orbited. Our sun, like all stars, generates energy through the process of nuclear fusion in its core, converting hydrogen into helium. This process has been constant for billions of years, but the rate of fusion slowly increases as the star ages and its core becomes denser and hotter. 3.8 billion years ago, our sun was about 70 to 75% as luminous as it is today. This simple fact presents a gentle but profound puzzle for planetary scientists, known as the faint young sun paradox. with significantly less energy reaching the planets. The habitable zone, the region where temperatures are just right for liquid water to exist on a planet's surface, would have been much smaller and closer to the Sun than it is today. Based on the Sun's faintness alone, a world like the early Earth should have been a frozen ball of ice, with its oceans locked in a global glacier. Yet, the geological evidence on Earth from this time strongly suggests the presence of liquid water. And as we will soon see, there is compelling evidence that Mars, a planet even farther from the Sun, was also a wet world with rivers and lakes. How could these worlds have stayed warm enough to support liquid water under a fainter Sun? The solution to this paradox lies not in the star but in the planets themselves, specifically in their atmospheres. The young, rocky planets like Earth, Venus, and Mars had atmospheres that were far thicker and richer in greenhouse gases than they are today. These early atmospheres were likely dominated by carbon dioxide, with significant amounts of methane and water vapor, all powerful greenhouse gases. A greenhouse gas is a molecule that is transparent to the incoming visible light from the Sun, but is very effective at absorbing the outgoing infrared radiation, or heat, that is radiated back from the planet's surface. This process traps heat in the atmosphere, acting like a planetary blanket that keeps the surface much warmer than it would otherwise be. The atmospheres of the young planets were so rich in these gases that this blanketing effect was exceptionally strong. On the early Earth, for example, the concentration of carbon dioxide may have been hundreds or even thousands of times higher than it is today. This created a powerful greenhouse effect that compensated for the weaker sunlight, keeping the average global temperature above the freezing point of water, and allowing the first oceans to remain liquid. So, when we picture these ancient worlds, we must imagine them not only under a dimmer sun but also wrapped in thick, insulating atmospheric blankets. It was this gentle partnership between the faint light of the young star and the thick air of the young planets that allowed for the possibility of a warm, wet, and perhaps even living solar system. While the young sun was fainter in its light output, it was far more energetic and volatile in other ways. Like most young stars, it had a much more powerful stellar wind and produced solar flares of an intensity that we rarely see today. The solar wind is a constant stream of charged particles, mostly protons and electrons, that flows outward from the sun's upper atmosphere, the corona. Today, this wind is a relatively gentle breeze, but in the sun's youth, it was a veritable gale, carrying away significantly more material from the star's surface. This powerful wind had a profound effect on the planets, especially those closest to the Sun. A planet's defense against the solar wind is its magnetic field. A magnetic field, generated by the motion of molten metal in a planet's core, creates an invisible shield called a magnetosphere that deflects the incoming charged particles. Worlds that had a strong global magnetic field, like the young Earth, were well protected. The solar wind was forced to flow around the magnetosphere, leaving the atmosphere largely untouched. But for worlds with weak or non-existent magnetic fields, this intense solar wind was a relentless force of erosion. Over millions of years, the gale of charged particles could effectively sandblast a planet's atmosphere, stripping it away layer by layer. The particles would collide with atoms in the upper atmosphere and impart enough energy to knock them out of the planet's gravitational grasp, sending them flying off into space. This process, known as atmospheric stripping, is believed to be one of the primary reasons why Mars, which once had a thick atmosphere, is today a world with only a thin, tenuous envelope of air. Its magnetic field, which was likely strong in its youth, eventually faded, leaving its atmosphere vulnerable to the relentless solar wind. In addition to this steady wind, the young sun was also prone to frequent and violent outbursts, known as solar flares and coronal mass ejections. These are sudden, immense releases of magnetic energy that send vast clouds of plasma and radiation hurtling out into the solar system. A flare from the young sun could have been thousands of times more powerful than the largest flares we observe today. For a planet caught in the path of such an eruption, the effects could be dramatic. The burst of radiation would bathe the planet, and the cloud of plasma would slam into its magnetosphere, causing spectacular auroral displays that might have covered the entire sky from pole to pole. On a planet without a protective magnetic field, these flares would have accelerated the process of atmospheric stripping and bathed the surface in high-energy radiation. This turbulent, energetic nature of the young sun was a defining feature of the early solar system, a constant and powerful force that actively shaped the atmospheres of the planets, protecting some and slowly eroding others, and in doing so, charting the course of their future evolution. Despite its faintness and its turbulent outbursts, the young sun's most fundamental role was, as it is today, to be the ultimate source of energy that governed the entire system. Even at 75% of its modern brightness, its light was the quiet engine driving the potential for change and complexity on every world. This light, this steady stream of photons traveling outward from the star's core, carried the energy that warmed surfaces, drove weather patterns, and, most profoundly, powered the chemistry that could lead to life. On the surface of a young, rocky planet with an ocean, the sunlight, though dimmer, penetrated the upper layers of the water. This energy could have been captured by simple molecules, driving chemical reactions and creating more complex compounds. This process, known as photochemistry, is a fundamental step in many theories about the origin of life. The sunlight provided the gentle, persistent energy needed to transform the simple organic molecules delivered by comets into the more intricate structures required for biology. The presence of light was a constant invitation for chemistry to become more interesting, more organized, and more complex. The sun's energy also created temperature differences across the planets, which in turn drove the circulation of their atmospheres and oceans. Air warmed at the equator would rise and move toward the poles, while cooler air would sink and return, creating global wind patterns. Ocean currents, driven by the same temperature gradients, would have circulated water around the planet, mixing the chemical ingredients of the primordial seas. This constant motion, all powered by the faint light of the distant sun, ensured that the young planets were not static places. They were dynamic systems, with energy flowing through them, creating environments of constant change and interaction. And so, we can see the young sun not as a weak or inadequate star, but as a perfectly suited parent star for a young solar system. Its faintness was gently counteracted by the thick greenhouse atmospheres of the planets, creating stable, warm conditions. Its powerful wind and flares were a test of planetary resilience, rewarding worlds with strong magnetic fields and sculpting the destinies of those without. And its steady, guiding light provided the essential energy for all the dynamic processes that would unfold on these worlds over the coming eons. The sun was the quiet center, the patient provider, the constant presence around which the entire story of the planets would gracefully unfold. It was the anchor of the system, and its light, however faint, was the spark that illuminated the path toward the future. Our planetary journey now begins in earnest, as we drift inward toward the world that lives closest to the sun's embrace. Here, just over a third of the distance from the sun as our own Earth, we find the small, dense planet Mercury. Today, it is a world of silent, extreme contrasts, but 3.8 billion years ago, it was a stage for some of the most dramatic events in the solar system's history. Imagine floating in the space near Mercury, with the young sun filling your view. From this vantage point, the sun appears nearly 3 times larger and 7 times brighter than it does from Earth. It is a brilliant, dominating presence, and its influence on this small world is absolute. The faintness of the young sun is less of a concern here. Mercury receives an abundance of energy, so much so that its dayside surface would have been incredibly hot, easily hot enough to melt lead. But this proximity also meant that Mercury bore the full, unfiltered brunt of the young sun's volatility. The powerful solar wind we spoke of was at its most intense this close to the star. A relentless gale of charged particles swept over Mercury constantly, a continuous and powerful cosmic sandblasting, and the immense solar flares, the sudden violent eruptions from the sun's surface, would have been devastatingly powerful here. Any world hoping to survive this close to the fire needed a strong defense, a robust magnetic field to deflect this onslaught. Remarkably, for its small size, Mercury did have such a defense. Deep within its core, the motion of liquid iron generated a magnetic field that, while weaker than Earth's, was strong enough to create a small bubble of protection, a magnetosphere that stood up against the solar wind. This magnetic shield was a crucial factor in Mercury's early survival, allowing it to hold on to a fragile, temporary atmosphere and preventing its surface from being eroded away completely. Mercury's orbit was also a defining feature of its existence. It completed a year, one full circle around the Sun, in just 88 Earth days. This swift journey meant that its surface was in a constant cycle of extreme heating and cooling. The side facing the Sun would bake under the intense radiation, while the side facing away, with no thick atmosphere to trap heat, would plunge into a profound cold. However, in this ancient past, Mercury's rotation on its axis was likely much faster than it is today. We now know a solar day on Mercury, the time from one sunrise to the next, is 176 Earth days long. But back then, it may have spun much more rapidly, perhaps completing a rotation in just a day or two. This faster spin would have created a more moderate temperature distribution, preventing the extreme, prolonged baking and freezing that characterize the planet today. It was a world living in a constant, rapid dance with the Sun, a dance of intense light, powerful radiation, and a silent, unending stream of particles from the heart of the solar system. As we draw closer to the surface of the young Mercury, we see a landscape that serves as a pristine, unblemished diary of the late heavy bombardment. With no significant atmosphere to burn up incoming objects, and no geological activity like plate tectonics to erase the evidence, every impact from that era was preserved with perfect, silent clarity. The surface of Mercury 3.8 billion years ago was a testament to this great cosmic storm, a canvas covered in countless craters of every size. From small, simple bowls to vast, complex basins hundreds of kilometers across. The defining event in Mercury's early history was a single, colossal impact. An asteroid, perhaps 100 kilometers in diameter, struck the planet with unimaginable force. The resulting explosion was so powerful that it sent seismic waves reverberating through the entire planet. On the exact opposite side of Mercury, the point antipodal to the impact, these focused seismic waves caused the ground to jolt upward, creating a bizarre, chaotic landscape of hills and fractures that planetary scientists now call the weird terrain. The impact itself gouged out an enormous basin, a crater over 1,500 kilometers wide, which we now know as the Caloris Basin. This single event was so massive it likely fractured the planet's crust and triggered a wave of volcanic activity. In the aftermath of the Caloris impact, and countless smaller ones, the surface of Mercury was a scene of both destruction and creation. The heat from these impacts, combined with the heat from the planet's own molten interior, turned vast regions of the surface into seas of liquid rock. These were not the dark, basaltic lava flows we see on our moon, but something different. Mercury's magma was likely richer in certain minerals, and as it flowed, it filled in the deepest craters and the lowest plains, creating smooth, flat surfaces known as the intercrater plains. These plains are one of Mercury's most distinctive features, vast expanses of ancient solidified magma that lie between the oldest, most heavily battered regions. As this global ocean of magma slowly cooled and solidified, the planet began to contract. The cooling of its massive iron core caused the entire planet to shrink in on itself, a process that continues on a much smaller scale even today. This global contraction caused the newly formed crust to wrinkle and buckle, like the skin of a drying apple. Enormous cliffs, some several kilometers high and hundreds of kilometers long, formed all over the planet's surface. These cliffs, known as lobate scarps, are another of Mercury's defining features. They slice through older craters and plains, a clear sign that they formed after the peak of the Great Bombardment. And so, the surface of young Mercury was a dynamic and evolving landscape, a world being simultaneously battered from above by the final salvos of the great cosmic storm, and reshaped from within by the cooling and shrinking of its own massive heart. It was a world forged in the crucible of both impact and internal heat, a process that created the scarred, wrinkled, and ancient surface we see today. To truly understand Mercury, we must journey beneath its scarred and battered crust, deep into its interior, for it is here that we find the planet's most remarkable and mysterious feature: its enormous iron core. For a planet so small, Mercury is only slightly larger than our own Moon. It is extraordinarily dense. This high density can only be explained if the vast majority of the planet's interior is made of metal. Modern measurements confirm that Mercury's iron-nickel core makes up about 60% of the planet's entire mass, and it is roughly the size of the Moon itself. In comparison, Earth's core accounts for only about 30% of its mass. This gives Mercury a truly unique structure among the planets. It is a massive ball of iron wrapped in a relatively thin shell of rock. How did this tiny world come to have such a disproportionately large iron heart? The answer likely lies in a violent event from an even earlier period of its history, before the late heavy bombardment. The leading theory suggests that the original, primordial Mercury was a much larger planet, perhaps twice its current mass, with a composition more similar to the other rocky worlds: a smaller core and a much thicker rocky mantle. Early in the solar system's history, this proto-Mercury was the victim of a colossal, grazing impact with another large planetary embryo. This was not a head-on collision that would have shattered both bodies, but a glancing blow. The impact stripped away a huge portion of proto-Mercury's lighter, rocky mantle, blasting it into space. The dense iron core, however, remained largely intact. Much of the vaporized rock from the mantle either escaped Mercury's gravity entirely or was swept up by the solar wind, while the remaining material eventually cooled and reaccreted onto the massive iron core, forming the thinner mantle and crust we see today. This giant impact hypothesis beautifully explains Mercury's strange, top-heavy composition. 3.8 billion years ago, this massive core was still largely molten and convecting vigorously. The swirling, flowing liquid iron acted like a giant dynamo, generating the magnetic field that was so crucial for protecting the planet from the young sun's fierce solar wind. This hot, liquid core was also the source of the volcanism that was reshaping the surface, with magma finding its way through cracks in the crust to flood the great impact basins and form the smooth plains. Mercury's story, then, is a story of its heart. It is a world defined by its core, a core so large it suggests a violent and traumatic birth, a core so hot it drove the geological activity that shaped its surface, and a core so dynamic it generated the magnetic shield that allowed this tiny world to endure its perilous dance so close to the fire of the young sun. Now we rise back to the surface of Mercury and consider the space just above it. Did this small, hot world have an atmosphere 3.8 billion years ago? The answer is both yes and no. Mercury could not hold onto a thick, permanent atmosphere in the way that Earth or Venus could. Its gravity was simply too weak, and its proximity to the sun meant that the solar wind was too strong and the surface temperature was too high. Any traditional atmosphere would have been quickly stripped away, or its gases would have boiled off into space. However, Mercury was not surrounded by a perfect vacuum. It possessed what is known as a surface-bounded exosphere. This is an incredibly thin, transient veil of atoms that are temporarily knocked off the planet's surface and briefly hop around before either falling back down or being lost to space. This was not an atmosphere you could breathe or in which you could see clouds, but a fleeting, almost imperceptible presence. This wispy exosphere was created and replenished by several processes. First, the intense solar wind, that constant stream of charged particles from the sun, would slam into the surface rocks. This process, called sputtering, would dislodge atoms of sodium, potassium, calcium, and magnesium from the minerals on the ground and send them bouncing into the space above. Second, micrometeoroids, tiny dust-sized particles that constantly rain down on all the planets, would strike the surface at high speeds. Each tiny impact would vaporize a small amount of rock, liberating more atoms and contributing them to the exosphere. The planet's own weak outgassing may have also played a small role, with volatile elements escaping from the interior through cracks in the crust. But this was a system in a delicate, temporary balance. The same forces that created the exosphere were also constantly destroying it. The pressure of the sunlight itself could push the atoms away, and the relentless solar wind would sweep them up and carry them away from the planet. An atom in Mercury's exosphere would only survive for a few hours at most before being lost. So, While we cannot picture young Mercury with a sky of blue or red, we can imagine it being surrounded by an ethereal, ever-changing halo of liberated atoms, constantly being created and just as constantly being swept away. This fleeting, wispy atmosphere was a direct consequence of Mercury's harsh environment, a world too small and too close to the sun to hold on to anything more substantial, a world whose only air was the dust of its own surface, briefly awakened by the sun's relentless energy. As our gentle exploration of the young Mercury draws to a close, we can reflect on this small world as a quiet and steadfast historian of the solar system, because it cooled down relatively quickly after its formation, and because it has lacked the dynamic forces of plate tectonics or significant atmospheric erosion for billions of years. Its surface has become a perfectly preserved museum of the ancient past. The story of the late heavy bombardment, the great cosmic storm that touched every planet, is written most clearly on the face of Mercury. When we look at the heavily cratered highlands of Mercury, we are looking at a surface that is essentially unchanged for nearly 4 billion years. Every pockmark, every basin, every overlapping scar is a record of an impact from that final formative era. The sheer density of these craters tells a story of a sky once filled with incoming rock and ice, a story that would have been true for the young Earth as well, but one that has been almost completely erased on our own world by the constant recycling of our crust and the weathering effects of wind and water. Mercury, in its geological silence, has held on to this memory for us. The Great Caloris Basin stands as a monumental tribute to the scale of the events of that time. It reminds us that the bombardment was not just a rain of small objects, but included impacts of a magnitude that is difficult to comprehend, impacts that could shake a planet to its core and reshape its entire geology. The smooth volcanic plains that fill Caloris and other large basins tell the next chapter of the story, a period of intense internal heat and volcanic activity that followed the great impacts, a common stage in the evolution of all rocky worlds. And the enormous wrinkled cliffs, the lobate scarps, tell a story of planetary cooling and contraction, a final, quiet settling after the heat and drama of formation. Mercury is a time capsule. It shows us, with startling clarity, the conditions that all the inner planets once endured. When we try to imagine the surface of the Hadean Earth or the young Mars, our best visual guide is the ancient, battered face of Mercury. It is a quiet reminder that every world in our solar system shares a common, violent, and creative heritage. It is the keeper of the solar system's oldest memories, a world that absorbed the final blows of creation and then fell into a deep geological slumber, preserving the evidence of that ancient storm for billions of years, waiting patiently for a time when a curious species from a neighboring blue planet would be able to look upon it and read its remarkable story. As we now gently drift away from this innermost world, we carry with us this image of a battered, ancient, and truthful landscape. Our journey now takes us outward from the Sun to the second planet, Venus. Today, Venus is a world of crushing pressure and searing heat, its surface hidden beneath a thick, impenetrable blanket of sulfuric acid clouds. It is often called Earth's twin because of its similar size and mass, but it is a twisted, hellish twin. Yet, 3.8 billion years ago, this may not have been the case. As we approach the young Venus, we must set aside our knowledge of its present state and open our minds to a gentle, tantalizing possibility, the story of a different Venus, a world that may have once been the most habitable place in the entire solar system. Floating in orbit around the young Venus, we see a world that looks comfortingly familiar. It is a beautiful blue and white marble, much like our own Earth. Its size, its density, and its rocky composition are all so similar to our home planet that it is easy to see them as siblings, born from the same part of the solar nebula and made of the same essential ingredients. 3.8 billion years ago, the profound differences that now separate the two worlds had not yet fully emerged. Their paths had not yet diverged. The young Venus was in a much more favorable position than Mercury. It was farther from the Sun, receiving only about twice the solar energy as Earth, an amount that could be managed by a suitable atmosphere. More importantly, it was large enough to have a hot, convecting core that likely generated a strong, protective magnetic field, just like Earth's. This magnetic shield would have deflected the young sun's powerful solar wind, allowing the planet to hold onto a substantial atmosphere and, crucially, to keep its water. The key to Venus's early promise lay in its atmosphere. While it was likely very rich in carbon dioxide, released by the same volcanic processes that were occurring on Earth, it was probably not yet the incredibly dense, crushing atmosphere it is today. Computer models of early planetary climates suggest that if Venus had a rotation period that was slow, perhaps slower than it is even today, and a significant amount of cloud cover, its surface temperatures could have been surprisingly moderate. The thick clouds would have reflected a large portion of the incoming sunlight back into space, a phenomenon known as a high albedo, which would have helped to counteract the greenhouse effect of the carbon dioxide. Under these conditions, with the faint young sun providing less energy and a reflective cloud layer balancing the atmospheric heat trapping, the surface of the young Venus could have maintained temperatures suitable for liquid water. This is the great what-if of our solar system's history. For hundreds of millions, perhaps even for 1 billion years or more, Venus may have been a temperate, watery world. It was Earth's twin not just in size, but potentially in climate as well. It was a world of possibility, a place where the conditions for life may have been just as favorable, if not more so, than they were on the young Earth. As we prepare to descend through its ancient clouds, we are not visiting the inferno we know today, but a lost paradise, a gentle world of oceans and volcanoes, a world on the cusp of a long, slow journey toward a very different destiny. Let us now drift down into the upper layers of Venus's ancient atmosphere. The sky above us is likely not a clear blue, but a bright, hazy white. A thick layer of water vapor clouds would have perpetually shrouded the planet, reflecting the dim sunlight and casting a soft, diffused light over the entire world. There would be no harsh shadows, just a gentle, even illumination from horizon to horizon. This sky was the key to Venus's early temperate climate. The atmosphere itself would have been composed primarily of carbon dioxide and nitrogen, much like the early Earth's. Carbon dioxide is a powerful greenhouse gas, and there was certainly enough of it to keep the planet warm under the faint young sun. However, 3.8 billion years ago, the processes that would lead to Venus's runaway greenhouse effect had likely not yet taken hold. A runaway greenhouse effect occurs when a planet's atmosphere traps so much heat that its oceans begin to boil away. The extra water vapor in the atmosphere traps even more heat, which causes the oceans to boil faster, creating a devastating feedback loop that continues until the oceans are gone and the surface temperature is incredibly high. But for this to happen, a critical temperature threshold must be crossed. In Venus's youth, several factors may have kept it safely below this threshold. The sun was fainter, providing less initial energy to the system. The planet's slow rotation, if it was indeed slow back then, would have also helped. A slow rotation allows for a thick cloud layer to build up on the day side of the planet, which acts like a bright, reflective shield, bouncing sunlight back into space before it can be trapped by the greenhouse gases below. This is a powerful, self-regulating mechanism that can keep a planet's climate stable. So, the atmosphere of the young Venus was one of delicate balance. The greenhouse effect of the carbon dioxide provided the necessary warmth, while the reflective water clouds provided the necessary cooling. It was a balance that allowed the planet to maintain a stable, temperate climate for a very long time. Breathing this air would have been impossible for us, of course, as it contained no free oxygen. But it was an atmosphere that could support liquid water. And that was the most important ingredient for the story that might have been unfolding on the surface below. It was an atmosphere of promise, a protective blanket that nurtured a world of serene global oceans under a soft, perpetually overcast sky. It was the atmosphere of a world that was, for a time, a true sibling to our own. Descending through the thick, white clouds, we break through the final layer of haze and find ourselves looking out over a breathtaking and profoundly moving sight. A global ocean. The surface of the young Venus, 3.8 billion years ago, may have been almost entirely covered in liquid water. The evidence for this lost ocean comes from modern-day measurements of the Venusian atmosphere. Venus has an unusually high ratio of deuterium to hydrogen. Deuterium is a heavier isotope of hydrogen, and because it is heavier, it is less likely to escape from a planet's gravity. The high concentration of deuterium today suggests that Venus once had a vast amount of water and that the lighter hydrogen atoms were stripped away into space over billions of years, leaving the heavier deuterium behind. Let us imagine these ancient seas. They would not have been the deep blue oceans of Earth, with their vast abyssal plains. The geology of Venus does not seem to have ever supported plate tectonics, the process that creates deep ocean basins and high continental landmasses on Earth. Instead, the Venusian landscape was likely more uniform, a single global crust. The oceans, therefore, would have been vast but relatively shallow, a global sea perhaps only a few kilometers deep, covering the entirety of the planet's lowlands. Any land that existed would have been the peaks of immense volcanoes, rising like scattered islands from the serene, planet-spanning waters. The water itself would have been warm, heated from below by the planet's internal heat, and from above by the gentle, greenhouse-warmed atmosphere, and it would have been rich in dissolved minerals and chemicals. The thick carbon dioxide atmosphere would have made the water slightly acidic, which would have efficiently dissolved minerals from the volcanic rock of the seafloor. And into this warm, mineral-rich water, the constant rain of comets and carbonaceous asteroids during the late heavy bombardment would have delivered a precious cargo of organic molecules. Here, in these shallow, sunlit and chemically rich seas of ancient Venus, the conditions for the origin of life may have been perfect. Picture this world, a place of profound and gentle calm. Under a perpetual bright white sky, a warm, shallow ocean stretches to every horizon. There is no wind of any great strength, as the slow rotation of the planet would not generate powerful storms. The only sounds are the gentle lapping of water against the volcanic islands and the distant rumble of a shield volcano releasing more gases into the thick, quiet air. It is a tranquil, peaceful world, a global greenhouse spa. For hundreds of millions of years, Venus may have been this paradise, a world far more clement and stable than the Hadean Earth, which was still reeling from the impact that formed its moon. In this moment, 3.8 billion years ago, if you were to search for the most likely cradle of life in our solar system, you would almost certainly have chosen the serene, watery surface of the young Venus. It is a vision of a lost world, a poignant reminder of how planetary destinies can diverge, and how a paradise can, over the eons, be lost. Even in this tranquil, oceanic paradise, the internal heat of the young Venus was making its presence felt on the surface. Like all the rocky worlds, Venus formed hot, and 3.8 billion years ago, it was still a geologically active planet, venting its interior heat through widespread volcanism. The land masses that rose above the shallow global ocean were likely not continents in the earthly sense, but massive shield volcanoes, similar to the Hawaiian Islands, but on a much grander scale. The volcanism on Venus was driven by plumes of hot mantle material rising from deep within the planet. When these plumes reached the base of the crust, they would spread out, causing the surface to bulge upward and fracture. Magma would then rise through these fractures, erupting onto the surface not in violent explosions, but in slow, steady flows of basaltic lava. These lava flows, over millions of years, would build up the immense volcanic structures that dotted the planet. This volcanic activity played a crucial and complex role in shaping the destiny of Venus. On one hand, it was a creative and stabilizing force. The volcanoes were the source of the planet's atmosphere, releasing the carbon dioxide, water vapor, and nitrogen that formed the thick, protective blanket that kept the planet warm and its oceans liquid. This outgassing was essential for maintaining the delicate climatic balance of the young world. The volcanic activity also recycled important chemicals, bringing minerals from the planet's interior to the surface where they could dissolve in the oceans and provide the raw materials for potential life. The volcanic islands themselves would have been places of incredible chemical activity, with hot springs and hydrothermal vents creating energy-rich environments, just like the deep-sea vents on Earth where many scientists believe life may have begun. On the other hand, this same volcanic activity contained the seeds of the planet's future demise. Every eruption released more carbon dioxide into the atmosphere. In the beginning, this was beneficial, helping to counteract the faintness of the young sun. But it was a process that could not continue forever. Unlike on Earth, Venus did not have plate tectonics or a carbon cycle that could efficiently remove carbon dioxide from the atmosphere and lock it away in carbonate rocks. On Earth, carbon dioxide dissolves in rainwater, reacts with rocks, and is eventually carried to the ocean floor and subducted back into the mantle. This acts as a global thermostat, regulating the planet's temperature over geological timescales. Venus had no such thermostat. The carbon dioxide released by its volcanoes simply accumulated in the atmosphere, slowly but relentlessly. For now, the planet's climate was stable, but the volcanoes were quietly, patiently, and inexorably adding to the atmospheric blanket, setting the stage for a future time when the sun would grow brighter, and the delicate balance would finally and catastrophically break. As we prepare to leave this ancient watery Venus, we are left with a quiet and profound sense of contemplation. Here was a world so remarkably similar to our own, a true sibling planet born from the same cosmic dust. For a time, it may have been the more promising of the two worlds, a tranquil, stable haven while the Earth was still a chaotic and violent place. But deep within the subtle differences between them, their two very different destinies were already written. The fundamental difference was a simple matter of location. Venus was born just a little too close to the sun. In the solar system's youth, under a dimmer star, this proximity was not a fatal flaw. It was a difference that could be balanced by cloud cover and atmospheric dynamics. But the sun, like all stars, was destined to grow brighter over the eons. The slow, steady increase in solar luminosity was an unchangeable fact of stellar evolution. For Earth, this gradual warming would be manageable. Its geological thermostat, the carbon cycle driven by plate tectonics, would adjust, removing more carbon dioxide from the atmosphere to keep the climate stable. Venus had no such ability to adapt. Its fate was sealed by its static, one-plate geology. The volcanoes would continue to add carbon dioxide to the air, and there was no efficient way to remove it. As the sun grew brighter, the temperature on Venus would inevitably rise. Slowly, patiently, the planet was approaching the critical threshold where the runaway greenhouse effect would begin. The oceans would start to evaporate, adding more water vapor, a powerful greenhouse gas, to the air, which would trap more heat and accelerate the evaporation in a vicious, unstoppable cycle. And so, we leave Venus at this poignant moment in its history, a beautiful, temperate water world, but one whose fate is already hanging in the balance. It is a world on a diverging path from our own. We have witnessed its period of greatest promise, its time as a serene, oceanic world veiled in gentle white clouds. The journey from this paradise to the inferno of today would take billions of years, a slow and gradual transformation driven by the brightening of its star and the patient, relentless outgassing of its own interior. As we drift away, we carry with us the memory of this lost ocean world, a quiet and sobering reminder of the delicate balance of factors that allows a planet to become, and to remain, a home for life. Our journey now brings us to our own home, the third planet from the Sun. But the Earth of 3.8 billion years ago is an alien world, a place we would not recognize. We are arriving at the very end of the Hadean Eon, a time of immense heat and constant change. The great cosmic storm is beginning to subside, but our young planet is still glowing with the fierce energy of its creation. It is a world in transition, leaving behind its fiery birth and just beginning to set the stage for the immense story of life that is to come. As we approach our young home, two features dominate the view. The first is the moon. It hangs in the sky not as the familiar, distant silver coin, but as a huge, imposing disk, perhaps 2 or 3 times larger than it appears today. It was born from a cataclysmic impact between the proto-Earth and a Mars-sized object, and in this ancient epoch it orbited much, much closer to our planet. Its gravitational pull was immense, raising colossal tides not in the oceans which were just beginning to form, but in the planet's molten rock surface itself. The moon's powerful presence was a constant, shaping force, a silent partner in Earth's earliest days. The second striking feature is the speed of the planet's rotation. The same giant impact that formed the Moon sent the young Earth spinning furiously on its axis. A day on the Hadean Earth was not 24 hours long, but perhaps as short as 5 or 6 hours. This rapid spin would have created a much stronger Coriolis effect, leading to incredibly powerful winds and storm systems in the nascent atmosphere. The planet was a blur of motion, a rapidly spinning sphere under the watchful gaze of its oversized companion. The surface itself is a dramatic landscape of fire and darkness. This is a world still releasing the tremendous heat of its accretion and the decay of radioactive elements within its core. The crust is thin and unstable, constantly being broken apart and recycled back into the molten mantle below. Vast oceans of magma glow with a dull, cherry-red heat, while darker, slightly cooler patches represent the first, temporary pieces of solid crust. This is not a world of stable continents, but of small volcanic islands, dark and basaltic, adrift in a sea of liquid rock. From space, the night side of the Hadean Earth would not have been dark, but a mesmerizing, shifting patchwork of glowing red lines and pools, the fiery cracks in its thin new skin. The late heavy bombardment is still in its final stages, and the surface bears the fresh scars of this cosmic rain. We might see a brilliant flash of light on the planet's limb as another large asteroid or comet strikes, the impact momentarily creating a splash of incandescent rock that rivals the glow of the magma seas. Each of these impacts delivers more energy to the already hot surface, and some of the largest may have been powerful enough to vaporize any early oceans, sterilizing the planet and forcing the process of cooling and condensation to begin all over again. This is the world we have arrived at. A fast, spinning, fiery planet with a giant moon hanging in its sky. A place of constant, violent recycling, a crucible in which the foundations of our home were being forged. Let us now imagine ourselves standing on one of the small, dark volcanic islands that made up the only solid ground on the Hadean Earth. As we look up, the sky is a sight of strange and alien beauty. It is not the familiar blue we know, but a thick, dense and likely reddish-orange sky. The young atmosphere was completely devoid of free oxygen, the gas that scatters blue light so effectively in our modern sky. Instead, it was a mixture of gases released from the planet's interior by volcanoes. A process called outgassing. The air was composed mainly of nitrogen, just as it is today, but it was also filled with enormous quantities of carbon dioxide, water vapor, and significant amounts of methane and ammonia. The carbon dioxide levels were perhaps thousands of times higher than they are now, creating the powerful greenhouse effect that was so essential for keeping the planet warm under the faint young sun. The methane in the atmosphere, produced by geological processes, would have created a chemical haze that tinged the sky with a persistent orange or reddish color. The sun would appear as a small, pale disk, its light struggling to penetrate this thick, hazy veil. The weather in this dense, fast-spinning atmosphere would have been extreme. The huge temperature differences between the molten surface and the cold upper atmosphere, combined with the rapid rotation of the planet, would have generated winds of incredible speed and storms of a scale we can barely imagine. Hypercanes, monstrous continent-sized hurricanes, may have been a common feature, their swirling clouds of condensed water vapor and other compounds adding to the drama of the sky. And the rain that fell from these clouds was not the clean, fresh water we know. The atmosphere was rich in acidic compounds like sulfur dioxide, also from volcanoes, which would have dissolved in the water vapor to form a persistent, corrosive acid rain. This acid rain would have aggressively weathered the fresh volcanic rocks on the surface, breaking them down and releasing their minerals into the nascent oceans. Above it all, the oversized moon would dominate the sky, a huge, scarred face, its features clearly visible. It raced across the sky in a matter of hours, its powerful gravity pulling not only on the magma seas but also on the thick atmosphere, creating immense atmospheric tides that would have added to the turbulence of the weather below. This sky thick, reddish, hazy, filled with colossal storms, acid rain, and the silent, swift passage of a giant moon was the sky of our planet's infancy. It was an unbreathable, inhospitable, and yet profoundly important sky, as it held the very ingredients that would soon condense to form the first oceans. the cradle where the next chapter of Earth's story would begin. For millions of years, the young Earth's atmosphere was saturated with water vapor. This water came from two main sources. It was delivered to the planet by the steady rain of icy comets during the late heavy bombardment, and it was released from the planet's own interior, carried to the surface as steam in volcanic eruptions. For a long time, the surface of the planet was simply too hot for this water to exist as a liquid. Any water that tried to condense would have instantly boiled back into a gas, adding to the already thick, steamy atmosphere. The Earth existed in a state of a global, planet-wide sauna. But as the initial, intense heat of the planet's formation began to radiate away into space, and as the frequency of the largest, ocean vaporizing impacts began to decrease, the surface slowly and patiently cooled. Eventually, a critical threshold was reached. The surface temperature dropped just enough for the water vapor in the atmosphere to begin to condense into liquid droplets. And so, it began to rain. This was not a rain we can easily comprehend. It was a global, relentless downpour that may have lasted for thousands or even millions of years. Under the dim sun and the thick reddish sky, warm, acidic water fell continuously, cascading down the slopes of the dark volcanic islands and collecting in the lowest lying areas of the young crust. Basins and craters, still warm from their formation, began to fill. Slowly, patiently, the water level rose, and the small, separate pools and lakes began to merge, connecting to form the first, shallow seas. Eventually, these seas grew so vast they joined together to form a global ocean. But this primordial ocean was very different from the oceans we know today. The water was hot, perhaps close to boiling in some places due to underwater volcanic activity. It was acidic from the dissolved carbon dioxide and other volcanic gases in the atmosphere, and it was not blue but likely a murky olive-green or brownish color. The early crust was made of iron-rich volcanic rock, and the acidic rain would have leached enormous quantities of iron into the water. This dissolved iron gave the first oceans their strange greenish hue. There were no continents to break up this ocean, only the scattered volcanic islands that pierced its surface. It was a true water world, a planet almost entirely covered by a single, hot, acidic, iron-rich sea. Yet, within this seemingly inhospitable environment, something incredible was beginning to happen. The organic molecules delivered by comets were now dissolved in this warm, mineral-rich water. And on the seafloor, at the boundary between the hot rock of the planet's interior and the chemical-rich water of its new ocean, were hydrothermal vents. These were cracks in the young crust where superheated, mineral-laden water from below gushed into the ocean, creating incredible gradients of temperature and chemistry. These dynamic, energy-rich environments may have been the perfect incubators, the ideal natural laboratories for the complex chemistry that would in the quiet depths of this strange green ocean, eventually spark into the first life. The formation of this ocean was the single most important event in our planet's early history, the moment when Earth transformed from a ball of fire and rock into a living world in waiting. While the first oceans were beginning to fill the lowlands, the solid surface of the Hadean Earth was a landscape of constant dynamic change. The concept of stable continents as we know them simply did not exist. The planet's crust was a thin, fragile skin floating on top of a churning, molten mantle. This early crust was not the light, granitic rock that makes up our continents today, but was composed almost entirely of dark, dense volcanic rock called basalt, much like the modern ocean floor. Instead of large continents, the landmasses were likely small protocontinents or volcanic islands. These were formed by plumes of hot material rising from the mantle, which pierced the crust and erupted lava onto the surface. These islands were not permanent fixtures. The mantle beneath them was convecting so vigorously that the thin crust was constantly being pulled apart and pushed back down. A piece of crust might exist for only a few million years before it was subducted or dragged back down into the mantle, its rock remelted and recycled. The entire surface of the planet was in a state of continuous fiery renewal. The style of volcanism would have been different too. Without thick continental crust to get in the way, the magma from the mantle could reach the surface much more easily. Eruptions were likely less explosive and more effusive. with vast floods of highly fluid lava pouring out from long fissures in the ground, spreading out to form immense, flat plains of black volcanic rock. The landscape was one of low-lying, dark basaltic shields and vast cracked lava fields, all under a thick, hazy sky. This early dynamic crustal activity played a vital role in Earth's evolution. Every time a piece of crust was melted and reformed, it would undergo a process called fractional crystallization. As the magma cooled, different minerals would solidify at different temperatures. Lighter minerals, those rich in silica, would have tended to stay molten longer and accumulate at the top of magma chambers. Over millions and millions of years of this constant recycling and remelting, these lighter, silica-rich minerals were gradually separated from the denser, iron-rich ones. This was the very beginning of the process of differentiation that would eventually lead to the formation of the first true continental crust. The small, dark volcanic islands were slowly, patiently being refined into a new type of rock, the lighter, more buoyant granitic rock that would one day rise above the global ocean and form the first stable continents. The world of fire and rock was not just a chaotic landscape. It was a planetary-scale geological laboratory, slowly creating the very foundations upon which all future landscapes, and all future life, would be built. Even as the Earth was beginning to settle, forming its first oceans and its first crust, the final echoes of the late heavy bombardment were still reverberating through the system. The rain of asteroids and comets had lessened from its peak, but massive impacts were still a regular, if infrequent, feature of life on the Hadean Earth. These final, colossal impacts were events of almost unimaginable scale, and they played a profound role in shaping the planet's earliest environment. An impact from an asteroid several hundred kilometers in diameter would have been powerful enough to completely sterilize the planet's surface. The energy released would have been many thousands of times greater than the simultaneous detonation of every nuclear weapon on Earth today. The impact would have instantly vaporized the asteroid itself, along with a huge volume of the Earth's crust. A vast crater would be formed. But more importantly, the heat generated would have been enough to boil away a significant portion of the newly formed oceans. A thick, temporary atmosphere of superheated rock vapor and steam would have enveloped the entire planet, raising the surface temperature to thousands of degrees. Any life that might have started to form in the oceans would have been utterly extinguished. This cycle of devastation and renewal may have happened multiple times. Life may have started, only to be wiped out by a giant impact, and then had to begin all over again in the newly condensed oceans. This has led some scientists to suggest that the last universal common ancestor of all life on Earth today may not have been the first life form, but the sole survivor of a particularly intense impact event. A life form that perhaps found refuge in the deep crust or in hydrothermal vent systems, shielded from the surface devastation. But these impacts were also creative. They delivered more water and organic molecules to the planet, replenishing the ingredients for life. They also fractured the crust, creating pathways for heat and magma from the interior to reach the surface, driving volcanic activity and the creation of more hydrothermal vent systems. Each impact, in its own way, stirred the planetary pot, preventing the young Earth from becoming a static, unchanging world. And so, as the Hadean Eon drew to a close around 3.8 billion years ago, the Great Bombardment finally faded into a much lower, background level of occasional impacts. The planet was left scarred, but also enriched. The final impacts were the last chaotic acts of creation, the final tempering of the world that was to become our home. The stage was now truly set. The oceans were in place, the first hints of stable crust were forming, and the skies had finally, truly grown quiet. We now shift our gentle gaze from the fiery young Earth to its constant companion, the Moon. Hanging large and silent in the turbulent sky, the Moon was not just a passive observer of Earth's early history. It was an active participant and a crucial protector. 3.8 billion years ago, the Moon was a world in its own right, with its own geology and its own story, a story that is forever intertwined with our own. To understand the Moon of this era, we must first remember its proximity, orbiting perhaps as close as 1/3 of its current distance. The Moon exerted a powerful gravitational influence on the Earth. Its pull created immense tides in the Earth's magma oceans, a constant kneading and stretching of the young planet that generated enormous amounts of frictional heat, contributing to the Earth's molten state. This tidal interaction also acted as a brake on Earth's fast rotation, slowly and patiently lengthening the day, over billions of years from its initial 5 or 6 hours towards the 24 hours we know today. But the relationship was a two-way street. The Earth's gravity had an even more powerful effect on the smaller moon, locking its rotation so that the same face was always turned toward our planet. This is a phenomenon called tidal locking, and it happened very early in the moon's history. So, from the surface of the Hadean Earth, you would always see the same features on the moon's face, though it would appear much larger and cross the sky much faster. This ever-present watchful face of the moon was also serving as Earth's silent shield. In the final stages of the late heavy bombardment, the Earth-Moon system was navigating a region of space still filled with debris. The moon, with its own significant gravity, acted as a cosmic catcher's mitt, attracting and absorbing countless asteroids and comets that might otherwise have struck the Earth. We can see the evidence of this protective role written all over the moon's surface today. Its face is covered with craters, a dense and overlapping record of billions of years of impacts. Many of those scars are blows that our own planet was spared because of the moon's presence. The moon was therefore a silent witness to the most violent and formative period of Earth's history, and it carries the detailed record of that time. While the evidence of the great bombardment on Earth has been erased by erosion and plate tectonics, the moon, having no atmosphere and no geology to speak of for the last 3 billion years, has preserved that history for us. It is a shared history. Every crater on the moon represents a moment in time that was experienced by the Earth-Moon system as a whole. By studying the moon's battered surface, we can read the story of our own planet's chaotic youth. It is our oldest and most faithful historian, a constant, silent companion that bore the brunt of the storm and has carried the scars of that shared past ever since. As we gaze upon the tidally locked face of the young moon, the face that forever watches the Earth, we see a landscape dominated by immense, dark, circular features. Early astronomers looking through the first telescopes mistook these for seas and called them maria, the Latin word for seas. We know today that they are not filled with water, but with dark, hardened lava. 3.8 billion years ago, these vast features were in the process of being born, and their story is the central story of the moon's geological history. The maria began their lives as colossal impact basins. During the peak of the late heavy bombardment, the moon was struck by a series of truly enormous asteroids, some of them hundreds of kilometers in diameter. These impacts were so powerful they punched clean through the moon's relatively thin crust, creating vast multi-ringed basins. We can still see their names on lunar maps today. Mare Imbrium, the Sea of Rains; Mare Serenitatis, the Sea of Serenity; Mare Tranquillitatis, the Sea of Tranquility, where the first humans would one day land. Each of these was the site of an impact that would have shaken the entire moon to its core. The immediate aftermath of one of these basin-forming impacts would have been a scene of unimaginable violence. A sea of molten rock would have filled the floor of the newly formed basin, which would have been surrounded by towering mountainous rings of uplifted crust. For a time, these basins were simply vast, fresh scars on the lunar surface, the largest and deepest of all the craters from the Great Storm. But the story of the maria was not just about impact. It was also about what happened next. From deep within the moon's own interior, the moon, like the Earth, had formed hot. Its interior was still partially molten, and radioactive decay was generating a great deal of heat. The colossal impacts that created the basins also fractured the lunar crust deep down, creating pathways for the magma from the molten mantle to eventually reach the surface. However, this did not happen immediately. There was a delay, a quiet period of 100 million years or more between the formation of the basins and the volcanic activity that would later fill them. So, at the precise moment of 3.8 billion years ago, many of the great basins on the near side of the moon were vast, empty, and relatively fresh depressions in the landscape. They were the deep, echoing scars of the bombardment's most powerful blows, waiting patiently for the next chapter of their story to begin. a chapter that would see them slowly and quietly filled from below by a sea of a very different kind. A sea of dark, silent, flowing rock. This two-act process of violent impact from above, followed much later by a quiet welling up from below, is what created the iconic face of the man in the moon, the pattern of light highlands and dark maria that has captivated human imagination for millennia. It is easy to think of the moon as a dead world, a place where nothing has happened for billions of years. And while that is largely true today, 3.8 billion years ago, the moon was still a geologically active planet in its own right. The heat from its formation and from the decay of radioactive elements in its core and mantle kept much of its interior in a molten or partially molten state. This internal heat was the engine that drove a period of widespread and long-lasting lunar volcanism. The great basin-forming impacts had deeply fractured the lunar crust, creating conduits for the magma from the deep mantle to begin its slow ascent to the surface. This magma was basaltic, similar in composition to the lava that erupts in Hawaii, but it was likely much less viscous, flowing almost like water. When this magma finally reached the floor of the great impact basins, it did not create towering volcanoes. Instead, it erupted from long fissures, or cracks, in the basin floor, spreading out in vast, thin sheets. This process, known as flood volcanism, happened in episodic pulses over a period of nearly 1 billion years. One eruption would lay down a thin layer of dark lava across the basin floor. After a long period of quiet, another eruption would occur, covering the first layer with a new one. Slowly, layer by layer, the immense deep basins were filled with these dark, iron-rich basaltic flows. This is why the maria appear so smooth and flat compared to the ancient, heavily cratered highlands. The lava flows buried all the older craters within the basins, creating a fresh, new surface. At our moment in time, 3.8 billion years ago, this process of mare volcanism was just getting underway. The oldest lava flows were beginning to pool in the deepest parts of the basins like Tranquillitatis and Serenitatis, dark patches spreading slowly across the grey, cratered floor. The peak of this lunar volcanic activity was still to come, but the moon was clearly a world with a hot and active interior. We can also see other evidence of this geological activity. As the lava flows cooled and contracted, they would sometimes form long, winding channels called sinuous rills, which look like dried-up riverbeds. These were likely lava tubes or channels whose roofs later collapsed. In other places, the cooling and settling of the thick layers of basalt caused the surface to wrinkle and buckle, creating long, low ridges called wrinkle ridges that meander across the surface of the maria. The young moon was not a static, silent place. It was a world in the midst of its most profound geological transformation, a world where the scars of the great bombardment were slowly, patiently, and beautifully being healed by the warmth of its own heart. One of the most defining characteristics of the moon, both then and now, is its almost complete lack of an atmosphere. Its gravity is simply too weak to hold on to a substantial envelope of gas. Any gases released by volcanic eruptions or delivered by comet impacts would have quickly escaped into space, stripped away by the solar wind or simply drifting away due to the low escape velocity. This absence of air had a profound effect on the lunar environment and is the primary reason why the moon has served as such a perfect historical record. Without an atmosphere, there is no weather. There is no wind to erode rocks, no rain to wash away features, and no clouds to obscure the sky. The lunar surface exists in a pristine, unfiltered vacuum. This means that every detail of the landscape, from the largest basin to the smallest crater, is preserved with incredible clarity. The sunlight on the moon is harsh and direct, creating sharp black shadows with no atmospheric haze to soften them. The temperature swings are extreme, from scorching hot in direct sunlight to incredibly cold in the darkness, with no air to moderate the changes. The sky from the surface of the moon would have been a sight of stark and absolute beauty. It was a perfect, unchanging black. Even during the day, the sun was a brilliant, sharp-edged disk, and the stars would have been visible at all times, not twinkling but shining with a steady, unwavering light. And hanging in that black sky was the most spectacular object of all, the Earth. 3.8 billion years ago from the lunar surface, the Earth would have appeared as a huge, brilliant star, much larger and brighter than the Moon appears to us. It was a stunning, marbled sphere of glowing red magma oceans, dark basaltic crust, and swirling thick, reddish-orange clouds. And because the Moon is tidally locked, the Earth would not have risen or set, but would have hung in the same position in the sky, slowly rotating on its axis, revealing its fiery, dynamic face. It was the ultimate celestial clock, a constant reminder of the vibrant, active world next door. This lack of an atmosphere also meant that the Moon's surface was completely exposed to the relentless rain of impacts, both large and small. There was no atmospheric shield to burn up even the smallest micrometeoroids. Every single grain of dust from space struck the surface at full cosmic velocity, contributing to the slow, steady churning of the top layer of lunar soil, a process called impact gardening. The Moon's face was a direct record of the cosmic environment, a silent, unfiltered witness to the history of the solar system, written in the language of craters and dust. The profound and intimate relationship between the Earth and its Moon was not a static one. Even as the Moon stood silent watch, a slow and graceful change was underway, a process that continues to this very day. The Moon was slowly, almost imperceptibly, moving away from the Earth. This process is called tidal recession, and it is a beautiful and direct consequence of the gravitational dance between the two worlds. It all begins with the tides. The Moon's gravity pulls on the Earth, creating tidal bulges. On the Hadean Earth, these were not just ocean tides, but colossal tides in the molten rock of the planet's surface. Because the Earth was spinning much faster than the Moon was orbiting, these tidal bulges were always slightly ahead of the Moon in its orbit. This leading bulge of mass then exerted its own gravitational pull on the Moon, gently tugging it forward in its path. This constant forward tug had the effect of boosting the Moon into a slightly higher, and therefore slower orbit. It was like giving the Moon a very gentle, continuous push, causing it to spiral slowly outward. This transfer of energy had a corresponding effect on the Earth. Just as the Earth was pushing the Moon away, the Moon was pulling back on the Earth's tidal bulges, acting as a brake. This braking action is what caused and still causes the Earth's rotation to slow down, gradually lengthening our day. The angular momentum that the Earth loses from its spin is transferred directly to the Moon's orbit. The entire Earth-Moon system is a closed gravitational partnership, with the Earth's day getting longer as the Moon's orbit gets larger. 3.8 billion years ago, with the Moon much closer to the Earth, this process of tidal recession was happening at a much faster rate than it is today. The Moon was retreating from the fast-spinning Earth quite rapidly, its orbit growing, and its appearance in the sky slowly shrinking over the millions of years. This slow retreat is a quiet, cosmic clock that measures the deep history of our two worlds. By understanding this process, astronomers can wind the clock backward and calculate how close the Moon was at different points in the past, confirming that it must have formed incredibly close to the Earth. So, as we take our leave from the young Moon, we imagine this slow, graceful separation. It is a quiet and poignant departure. The two worlds, born together in a single violent cataclysm, were now beginning their long, slow drift apart. The Moon would continue its role as Earth's protector and historian, but from an ever-increasing distance. Its gravitational grip on our planet would lessen, the tides would become less extreme, and its apparent size in our sky would slowly diminish, a silent, gradual retreat into the beautiful, familiar celestial companion we know tonight. Our journey now carries us outward, past the Earth-Moon system, across the great expanse that separates us from the next world. We arrive at the fourth planet from the Sun, Mars. Today we know Mars as the Red Planet, a cold, dry, desert world with a thin atmosphere. But as we approach the Mars of 3.8 billion years ago, we see a world transformed, a planet that may have been, for a time, the most Earth-like world in the entire solar system. Gazing at the young Mars from orbit, we are struck by its color. It is not uniformly red, but a rich tapestry of ochre, gray, and most stunningly blue. This was a world with a substantial atmosphere, and most importantly, with large, stable bodies of liquid water on its surface. For a brief, shining moment in cosmic history, our solar system may have had 2 blue planets. The Mars of this era was a world on the outer edge of the habitable zone, the region where temperatures could allow for liquid water. Under the faint young sun, it should have been a frozen world. But like the early Earth and Venus, Mars was wrapped in a much thicker atmosphere than it has today, an atmosphere rich in carbon dioxide that created a significant greenhouse effect. This atmospheric blanket trapped enough of the sun's faint warmth to raise the surface temperature above the freezing point of water, at least in the planet's equatorial regions. This warmer, wetter Mars was also a more geologically active Mars. In its youth, the planet's interior was still hot, and this heat was driving both a global magnetic field and widespread volcanism. The magnetic field was crucial. It would have provided a shield against the young sun's powerful solar wind, protecting the atmosphere from being stripped away into space. This shield allowed the atmosphere to remain thick enough to maintain the pressure needed for liquid water to be stable on the surface. Without that magnetic field, the water would have quickly boiled away into the thin air. The evidence for this ancient watery Mars is carved into the landscape we see today. Orbiters have mapped vast, dried-up river channels that meander for hundreds of kilometers, intricate delta fans where these rivers emptied into larger bodies of water, and the distinct, terraced shorelines of ancient lakes that once filled colossal impact craters. The landscape is a fossil, a perfectly preserved testament to a time when water flowed freely across the Martian surface. As we prepare to descend to this ancient world, we are visiting not a desert, but a vibrant, dynamic planet of rivers, lakes, and perhaps even a great northern ocean, a world that for a time held as much promise for life as our very own. Let us now descend into the atmosphere of the young Mars. The sky here is likely not blue but a pale butterscotch or pinkish color. The air is filled with fine, reddish dust from the iron-rich surface, which scatters the sunlight in a way that gives the sky its warm, gentle hue. The atmosphere itself is much denser than the thin envelope of air on Mars today, perhaps as thick as Earth's modern atmosphere, or even thicker. This atmosphere was composed almost entirely of carbon dioxide, which was continuously supplied by the planet's active volcanoes. This high concentration of CO2 was the key to the planet's warmth. It created the powerful greenhouse effect that trapped the faint sunlight and kept the surface temperatures from plunging below freezing. Water vapor, evaporated from the surface lakes and rivers, would also have been a significant component, adding to the greenhouse effect and creating a stable water cycle of evaporation, condensation into clouds, and precipitation. We can imagine fluffy, white water ice clouds drifting through the pale pink sky, casting soft shadows on the landscape below. It may have rained or even snowed in the higher latitudes and on the peaks of the great volcanoes. This was a world with weather, with seasons, and with a dynamic climate system. And all of this was protected by the planet's magnetic field, generated by a churning liquid iron core deep within the planet. The Martian magnetosphere would have stood up to the young sun's solar wind, deflecting the charged particles and shielding the atmosphere from erosion. This protective bubble was the unsung hero of the early Martian climate, the invisible force that allowed the planet to hold onto its air and its water, and to maintain its habitable conditions for hundreds of millions of years. The atmosphere of young Mars was therefore a fragile but beautiful system. It was a delicate balance between the volcanic outgassing that supplied the greenhouse gases, the magnetic field that protected them, and the faint sunlight that they trapped. For a time, this balance held, creating a world that was tantalizingly similar to our own. It was an atmosphere that sustained a water cycle, that painted the sky with clouds, and that wrapped the planet in a gentle, protective warmth, creating a brief, golden age for the red planet, a time when it was a world of serene and life-giving possibility. Now, we find ourselves on the surface of this ancient Mars, standing on the shore of a vast, calm body of water. The landscape around us is a panorama of reddish-brown rock and soil, but it is a landscape transformed by the presence of water. We can hear the gentle lapping of waves against the shore and feel a cool, gentle breeze coming off the lake's surface. This is the Mars of the Noachian period, its brief but beautiful springtime. The evidence for this watery past is overwhelming. and is written in the very geology of the planet. All across the southern highlands, we can trace the paths of ancient river systems. Some are small dendritic networks of channels that look like the tributaries of a terrestrial river. Others are enormous outflow channels, carved in what must have been catastrophic floods, perhaps when the walls of a large crater lake were breached, releasing a torrent of water that scoured the landscape for hundreds of kilometers. These rivers flowed downhill, following the contours of the land, and pooled in the lowest lying areas, which were often the floors of large impact craters. Craters like Gale and Jezero, which are being explored by our rovers today, were once deep, tranquil lakes, filled with water for millions of years. We can see the evidence in the layers of sediment that were deposited on the lake floors, and in the beautifully preserved deltas that formed where rivers emptied into the Bros. Still water, dropping their load of sand and mud. But the most breathtaking possibility is that these rivers and lakes were all part of a single, global hydrological system that fed into a vast ocean covering the northern hemisphere of the planet. The northern third of Mars is significantly lower in elevation than the southern highlands, forming a huge basin known as the Vastus Borealis. Many scientists believe that this basin was once filled with water, creating a primordial ocean that would have been similar in size to the Arctic Ocean on Earth. Let us imagine standing on the ancient shoreline of this great Oceanus Borealis. Before us, a vast expanse of water stretches to the horizon, its surface ruffled by a gentle breeze under the pale pink sky. The air smells of wet earth and volcanic minerals. In the distance, the colossal shield of Alba Mons, an enormous volcano, rises into the clouds. Rivers snake down from the southern highlands, their mouths forming muddy, sprawling deltas along the coast. It's possible icebergs carved from glaciers in the polar regions would have drifted slowly across its surface. It is a scene of profound, quiet beauty, a scene that feels almost like home. For a period of perhaps several 100 million years, this was the reality of Mars. It was a dynamic water world, a planet of flowing rivers, placid lakes, and a great, cold northern sea. It was a world that had all of the necessary ingredients for life: liquid water, a source of energy, and a supply of organic molecules from comet impacts. Whether life ever did arise in these ancient waters is one of the most profound questions in all of science, a question that drives our continued exploration of this fascinating, faded world. In the western hemisphere of this ancient Mars, a vast region of the planet's crust was beginning to bulge upward, pushed from below by a massive plume of hot material rising from the deep mantle. This was the Tharsis region, and it was the site of the most spectacular volcanic activity in the entire solar system. Here, a series of colossal shield volcanoes were being born, volcanoes that would eventually dwarf any on Earth. Among them was Olympus Mons. 3.8 billion years ago, it was not yet the giant it would become, but it was already an active and immense volcano, steadily growing with each eruption. Because Mars lacks plate tectonics, these volcanoes could sit over the same hot spot in the mantle for hundreds of millions of years, allowing them to grow to truly staggering sizes. Lava, fluid and basaltic, would have flowed from the summit caldera and from long fissures on its flanks, spreading out to form the vast, gently sloping shield that characterizes these Martian volcanoes. This volcanic activity was the lifeblood of the young, wet Mars. The volcanoes of Tharsis were the primary source of the planet's atmosphere. With each eruption, they released enormous quantities of carbon dioxide, water vapor, and sulfur compounds into the air. This constant outgassing is what built and maintained the thick greenhouse atmosphere that kept the planet warm. The water vapor replenished the planet's water cycle, and the carbon dioxide kept the atmospheric pressure high enough for that water to remain liquid. The volcanoes also played a crucial role in recycling water and minerals. The immense heat from the underground magma chambers would have melted ground ice, creating vast reservoirs of liquid water deep within the crust. This water could then emerge at the surface as springs or in massive flood events, feeding the rivers that flowed across the planet. The lava flows themselves, when they cooled, would form fresh volcanic rock that could be weathered by the rain and wind, releasing essential minerals and nutrients into the surface water. The Tharsis region, with its towering active volcanoes, was the geological engine of the Noachian world. It was a place of immense power and creation, a constant source of the very gases and water that made the planet habitable. We can imagine looking up from the shores of a Martian lake and seeing the dark plume of an eruption from one of the distant Tharsis volcanoes, a silent, grey column rising high into the pink sky. It was a beautiful, symbiotic relationship. The volcanoes fed the atmosphere that allowed the water to flow, and the water, in turn, carved and shaped the volcanic landscape, creating a dynamic, evolving, and for a brief time truly habitable world. As we prepare to leave this beautiful blue Mars, we do so with a sense of quiet melancholy, because we know that this golden age was not destined to last. Even at this moment of its greatest promise, the forces that would lead to its demise were already in motion. The story of Mars is the story of a world that lost its warmth, and the change began deep within its core. Mars is a much smaller planet than Earth or Venus. Because of its smaller size, it has a larger surface area to volume ratio, which means it cooled down much more quickly after its formation. The heat engine in its core, the churning liquid iron that generated its protective magnetic field, began to slow down. As the convection in the core faltered, the magnetic field weakened, and eventually, it died almost completely. The timing of this is crucial. Around 3.8 billion years ago, the Martian dynamo was likely in its final stages. The magnetic shield that had protected the planet for hundreds of millions of years was beginning to fail. And as it failed, the atmosphere was left exposed and vulnerable to the full, relentless force of the young sun's solar wind. The process of atmospheric stripping began. The charged particles of the solar wind began to collide with the atoms and molecules in the upper Martian atmosphere, knocking them away into space, one by one. It was a slow, patient, and inexorable process of erosion. Without the volcanoes being able to replenish the atmosphere as fast as it was being lost, the air began to thin. As the atmosphere thinned, two things happened. First, the atmospheric pressure dropped. As the pressure fell, the boiling point of water decreased. Eventually, the pressure became so low that liquid water could no longer be stable on the surface. It would simply boil away into the thin air. Second, the greenhouse effect weakened. With less carbon dioxide to trap heat, the planet began to cool down. The rivers and lakes began to freeze over, and the water cycle slowly ground to a halt. The water that remained was locked away as ice in the polar caps and as permafrost beneath the surface. Mars was beginning its long, slow transition from a warm, wet world to the cold, frozen desert we see today. We are leaving Mars at the very cusp of this great change, the final beautiful moments of its watery past, a fading echo of a world that might have been, leaving the fading warmth of the inner solar system behind. Our journey now takes us into a vast, dark, and mostly empty region of space. This is the realm of the asteroids, a broad belt of rocky and metallic debris that circles the Sun between the orbits of Mars and Jupiter. Today, it is a place of quiet, lonely orbits. But 3.8 billion years ago, it was a much more dynamic and crowded place, the source of the great storm that had so recently sculpted the inner worlds. The asteroid belt marks a fundamental boundary in our solar system. It lies near the frost line, the theoretical distance from the young sun beyond which it was cold enough for volatile compounds like water to condense into solid ice. Inside the frost line, the rocky planets formed: Mercury, Venus, Earth, and Mars. Outside the frost line, the gas and ice giants formed. The asteroid belt is the transition zone between these two realms, a cosmic no-man's land populated by the leftovers of planetary formation. It is a common misconception, fueled by science fiction, that the asteroid belt is a crowded, treacherous field of tumbling rocks that one must carefully navigate. The reality is that space is incredibly vast, and the asteroid belt is incredibly sparse. While there are millions of asteroids in this region, the average distance between them is over 1 million kilometers. It is more of an empty desert than a crowded field. But 3.8 billion years ago, this region was significantly more populated. It contained many more objects, and perhaps several hundred times more mass than it does today. It was a rich repository of planetesimals, the small primordial bodies that were the building blocks of planets. These ranged in size from dust particles to objects hundreds of kilometers in diameter, and they were a diverse population reflecting their position astride the frost line. Those in the inner part of the belt were primarily rocky and metallic, the same material that formed the terrestrial planets. Those in the outer part of the belt were richer in water, ice, and carbonaceous materials, the same ingredients that would go on to form the cores of the giant planets. The asteroid belt was, and still is, a perfect sample of the raw materials of the entire solar system, neatly sorted by their distance from the Sun. It is the rubble left over from the construction of our planetary home, a quiet and orderly graveyard of worlds that were never born. Why did a planet never form in this region, so rich with building blocks? The answer lies just beyond the belt, in the colossal, looming presence of Jupiter. Jupiter is so massive that it contains more than twice the mass of all the other planets combined. Its gravitational influence is immense and far-reaching, and it has dominated the history of the asteroid belt from the very beginning. In the early days of the solar system, the planetesimals in the asteroid belt region began to accrete, just as they did elsewhere. They collided and stuck together, growing into larger and larger bodies, on their way to forming a fifth rocky planet. But the nearby presence of the rapidly growing Jupiter threw this process into chaos. Jupiter's gravity acted as a great cosmic stirrer, exciting the orbits of the planetesimals in the belt. It tugged on them, pulling their orbits from gentle circles into elongated, elliptical paths. This gravitational stirring had a profound consequence. It dramatically increased the relative velocities of the planetesimals. Instead of gently bumping into each other and merging, they began to collide at high speeds. These collisions were no longer constructive, but destructive. The planetesimals began to shatter and fragment, grinding each other down into smaller and smaller pieces. The process of planetary accretion was halted and then thrown into reverse. Jupiter's gravity ensured that a planet could never form here. Furthermore, Jupiter's influence created specific regions within the belt, where no object could maintain a stable orbit. These are known as the Kirkwood gaps, and they correspond to orbital resonances with Jupiter. For example, an asteroid at a distance where it would complete 3 orbits for every one of Jupiter's would be in a powerful 3-1 resonance. At each alignment, it would receive a gravitational kick from Jupiter, which would eventually destabilize its orbit and eject it from the belt. This process is what sculpted the asteroid belt into its modern, structured form, with distinct gaps and families of objects. Jupiter's gravitational hand has been the undisputed master of this realm, the shepherd that prevented a flock from ever becoming a world, and instead scattered it into the sparse, shattered remnant we see today. The asteroid belt was not just a region of failed planetary formation. It was also the primary arsenal for the late heavy bombardment that so profoundly shaped the inner planets. The same gravitational stirring from Jupiter that prevented a planet from forming was also responsible for sending a steady stream of rocky bodies careening into the inner solar system. But the true trigger for the Great Storm, the event that turned a steady trickle of impacts into a massive flood, was the migration of the giant planets. As we recall, the late heavy bombardment was initiated when Jupiter and Saturn crossed a powerful 2-1 orbital resonance. This event sent gravitational shockwaves throughout the entire solar system. In the asteroid belt, these sweeping resonances were particularly disruptive. They passed through the belt, exciting the orbits of vast numbers of asteroids and pushing them into the unstable Kirkwood gaps. Once in these gaps, Jupiter's relentless gravitational kicks would quickly eject them from the belt, sending them onto new paths that crossed the orbits of Mars, Earth, Venus, and Mercury. Suddenly, the inner solar system was flooded with a population of high-velocity, rocky impactors. These were the sculptors of the inner worlds, the source of the countless craters that pockmarked the surfaces of Mercury and the Moon. They were the source of the Bayesian-forming impacts that triggered volcanism and reshaped the early crusts of all the terrestrial planets. The asteroid belt, which had been a relatively quiet repository of building materials, was temporarily turned into a cosmic shooting gallery, with the inner planets as the targets. The composition of these impactors varied, depending on where in the belt they originated. Those from the inner belt were stony, S-type asteroids, made of silicate rock and metals. Those from the outer belt were carbonaceous, C-type asteroids, which were much darker and richer in carbon, organic compounds, and water bound up in their minerals. The delivery of these C-type asteroids was particularly important. Along with the comets from the even more distant Kuiper belt, they contributed to the supply of water and the chemical building blocks of life to the young Earth. The asteroid belt, in its moment of greatest disruption, was therefore a source of both destruction and creation. It delivered the violent impacts that scarred the planets, but it also delivered some of the essential ingredients that would allow one of those planets to eventually blossom with life. The Great Storm was a gift from this shattered realm, a final, convulsive contribution from the world that never was to the worlds that were just beginning their long and remarkable journeys. While Jupiter's gravity prevented the formation of a large planet, not all the bodies in the asteroid belt were small, shattered fragments. A few of the largest planetesimals, those that had grown rapidly in the very earliest days before Jupiter's influence became too disruptive, managed to survive. These were the protoplanets of the asteroid belt, small worlds in their own right, and 3.8 billion years ago, they were undergoing their own unique evolution. The largest of these is Ceres. At nearly 1,000 kilometers in diameter, Ceres was, and still is, large enough for its own gravity to pull it into a spherical shape, earning it the modern designation of a dwarf planet. In this ancient era, Ceres was likely a developing world. It had accreted early and hot, and the decay of radioactive elements within its interior would have generated enough heat to cause it to differentiate. This means that the heavier, rocky materials would have sunk to the center to form a core, while lighter materials, including a significant amount of water ice, would have risen to the outer layers. 3.8 billion years ago, it's possible that Ceres had a rocky core surrounded by a thick mantle of water ice, and perhaps even a liquid water ocean sloshing beneath its icy crust. It was an ocean world in miniature, a tiny cold sibling to the larger, more famous moons of the outer solar system. The second largest asteroid, Vesta, tells a different story. Vesta is a rocky body, and it too differentiated early in its history, forming a metallic core, a rocky mantle, and a basaltic crust. It was, in essence, a tiny terrestrial planet. For a brief period, Vesta was volcanically active, with lava flows erupting onto its surface. We know this because a family of smaller asteroids, and a specific type of meteorite that has fallen to Earth, can be traced back to Vesta, and these rocks are clearly volcanic in origin. By 3.8 billion years ago, the small Vesta had likely cooled, and its volcanism had ceased. But its surface was a record of this fiery, active past, a past that was now being heavily battered and cratered by the late heavy bombardment. These large bodies, Ceres, Vesta, and a few others like Pallas and Hygeia, were the winners in the asteroid belt, the few objects that grew large enough to become small worlds before the destructive grinding process took over. They were survivors, each with its own unique geological history, one a potential water world and the other a tiny ancient volcanic planet. They offer us a precious glimpse of what might have been, a frozen moment in the process of planetary formation, preserved for billions of years in the vast, quiet expanse between Mars and Jupiter. As we gently drift out of the asteroid belt and continue our journey outward, we can look back on this sparse, quiet region with a new sense of understanding. It is not just a field of debris, but a profound and invaluable historical archive. The asteroids are the most primitive, unaltered building blocks of the planets, and by studying them, we can learn about the conditions and the materials that existed at the very dawn of the solar system. The different types of asteroids, neatly sorted by their distance from the Sun, provide a perfect cross-section of the original solar nebula. The rocky S-types in the inner belt tell us about the materials that formed the terrestrial planets. The carbonaceous C-types in the outer belt, rich in water and organic molecules, tell us about the ingredients that were available to form life. And the rare M-type asteroids, which are almost pure nickel-iron, are the exposed cores of shattered protoplanets, giving us a direct look at the interiors of these ancient developing worlds. The asteroids are, in a very real sense, the remnants of a lost world, the planet that Jupiter's gravity prevented from ever forming. But in its failure to become a planet, the asteroid belt became something arguably more valuable to us. a perfectly preserved museum of planetary origins. Because most asteroids are too small to have undergone significant geological evolution, they have remained largely unchanged for 4.5 billion years. They are time capsules, carrying the chemical and isotopic fingerprints of the primordial solar system. When we study the meteorites that have fallen to Earth, which are fragments of these asteroids, we are holding in our hands the very stuff from which our world was made. They are our most direct link to the ancient past we have been exploring tonight. As we leave this shattered realm behind, we do so with a sense of gratitude for this quiet, unassuming belt of rock and ice. It is the ghost of a planet that never was, a silent record keeper that holds the secrets of our own beginning. Our journey now takes a great leap outward, into the realm of the giants. We arrive at the fifth and largest planet, the undisputed king of the solar system, Jupiter. This colossal world is a system in its own right, a place of immense scale, power, and turbulent beauty. 3.8 billion years ago, Jupiter was not just a passive member of the solar system. It was its primary architect and guardian, the gravitational anchor that shaped the destinies of all the other worlds. As we approach Jupiter, its sheer size is difficult to comprehend. This single planet contains more than 2.5 times the mass of all the other planets, moons, asteroids, and comets in the solar system combined. It is a world made not of rock and metal, but almost entirely of the two simplest and most abundant elements in the universe, hydrogen and helium, the same ingredients that make up the Sun. Jupiter is, in essence, a failed star. It grew massive enough to capture a huge atmosphere from the solar nebula, but it fell short of the threshold needed to ignite nuclear fusion in its core. 3.8 billion years ago, the young Jupiter was still settling down from its rapid and dramatic formation. It was still contracting under its own immense gravity, a process that generated a tremendous amount of heat. In this era, Jupiter was actually radiating more heat into space than it was receiving from the distant, faint Sun. It was a planet that glowed with its own internal energy, a faintly luminous, warm presence in the cold outer solar system. From a distance, it would have looked much as it does today, a majestic, banded sphere of swirling clouds. The distinct, colorful bands of light-colored zones and darker belts are created by the planet's incredibly rapid rotation. A day on Jupiter was, and still is, less than 10 hours long. This furious spin, combined with the heat rising from the interior, drives the planet's extreme weather, stretching the clouds into the parallel bands that circle the globe. The colors, the familiar whites, yellows, oranges, and browns, are the result of complex chemistry in the upper atmosphere, where trace compounds are churned up from the warmer depths and interact with sunlight. But this familiar scene was playing out under a different light. The Sun from Jupiter's orbit is a small, distant star, appearing only about 5% as bright as it does from Earth. The primary source of warmth for this young giant was its own internal furnace. It was a world that made its own climate, a self-sufficient kingdom ruled by its own heat and its own dizzying spin. It was the first of the giants to form, the great anchor of the solar system, and its colossal presence set the rules for all the worlds that followed. Let us now descend into the upper layers of Jupiter's immense atmosphere. We are entering a world of weather on a scale that dwarfs anything on Earth. The winds here are among the fastest in the solar system, with jet streams screaming past at speeds of over 500 kilometers per hour. The zones are regions of rising, cooling air, forming high-altitude clouds of white ammonia ice. The belts are regions of sinking, warming air, where we can see deeper into the atmosphere to the darker, more colorful cloud layers below. This entire, planet-spanning weather system is driven by the heat escaping from Jupiter's deep interior. It is a colossal convection engine, with warm gas rising and cool gas sinking on a global scale. This motion is then organized by the planet's rapid rotation into the familiar banded pattern. The result is an atmosphere of unimaginable turbulence and complexity. Within this turbulent flow, massive storms are born. These take the form of swirling vortices, or ovals, some of which can be thousands of kilometers across. We can see them churning at the boundaries between the belts and zones, giant, rotating weather systems that can persist for decades or even centuries. The most famous of these storms, the Great Red Spot, may have been present even this long ago. The Great Red Spot is a colossal anticyclone, a high-pressure storm system that has been raging in Jupiter's southern hemisphere for at least 300 years, and likely for much longer. It is a storm so large that 2 Earths could fit comfortably inside it. 3.8 billion years ago, a nascent version of this storm, or perhaps other similar giant vortices, would have been a prominent feature in the swirling cloud tops. We can imagine it as a great reddish-brown oval, a permanent planet-sized hurricane in the vast, turbulent ocean of Jupiter's atmosphere. Lightning would also be a common sight, but on a Jovian scale. Massive thunderstorms, fueled by the convection of water vapor from deep within the atmosphere, would generate superbolts of lightning 1,000 times more powerful than any on Earth. These would flash within the deep water clouds, their light diffusely illuminating the overlying cloud layers from below. The young Jupiter was a world of constant, violent, and beautiful atmospheric motion, a dynamic canvas of continent-sized storms, lightning, and planet-circling jet streams, all painted in hues of orange, white, and brown, and all powered by the immense heat of its own primordial heart. Jupiter's greatest role in the young solar system was not its weather or its internal heat, but the profound and far-reaching influence of its gravity. As the most massive object besides the Sun, Jupiter acted as the great shepherd and architect of the entire system, a role that was both destructive and protective. As we have seen, Jupiter's gravity was responsible for preventing a planet from forming in the asteroid belt. It stirred the orbits of the planetesimals, turning a process of gentle accretion into one of high-speed, destructive collisions. Its resonances carved the Kirkwood gaps, sculpting the belt into its modern form. This act of prevention was the first great step in shaping the solar system's architecture. Then came the period of planetary migration and the great resonance with Saturn, which triggered the late heavy bombardment. Jupiter's influence was the direct cause of this system-wide storm. Its gravity flung the asteroids from the belt and played a key role in destabilizing the orbits of the outer planets, which in turn sent a shower of comets plunging toward the Sun. Jupiter was the agent of chaos, the one who initiated the final violent act of planetary creation. However, Jupiter's role was not solely one of disruption. It also acted as the solar system's great guardian, its cosmic shield. For every one asteroid or comet that Jupiter's gravity sent hurtling toward the inner solar system, it captured or ejected many, many more. The planet's immense gravity creates a gravitational well so deep that it acts like a cosmic vacuum cleaner. Countless comets and asteroids from the outer solar system that might have otherwise threatened the inner planets were instead drawn toward Jupiter. Some of these objects were captured into orbit around Jupiter, becoming temporary or permanent moons. Many others plunged directly into the planet's thick atmosphere, their fiery entry a fleeting and insignificant event for the giant world. But the vast majority were simply ejected from the solar system entirely. A close pass by Jupiter would act as a gravitational slingshot, accelerating the smaller body to speeds that exceeded the Sun's escape velocity, sending it on a one-way journey into interstellar space. This protective role has been crucial for the development of life on Earth. By clearing the solar system of a huge amount of potentially hazardous debris, Jupiter dramatically reduced the long-term impact rate in the inner solar system. After the initial chaos of the late heavy bombardment had subsided, Jupiter's steady presence created a much safer, more stable environment where life could evolve, without the constant threat of sterilizing impacts. Jupiter is both the bringer of the storm and the guardian of the peace that followed. It is the shepherd of the solar system, a powerful and sometimes chaotic force that ultimately sculpted our planetary home and then stood watch over it, protecting it for the billions of years that followed. Just as the planets formed from a disk of gas and dust circling the young Sun, Jupiter's largest moons formed from a similar, smaller-scale disk that surrounded the young giant planet. As Jupiter grew and captured its massive hydrogen and helium atmosphere, it created a swirling, flattened sub-nebula of material in orbit around its equator. Within this disk, the process of accretion played out in miniature, giving birth to Jupiter's 4 largest and most famous moons, Io, Europa, Ganymede, and Callisto. These are not small, captured asteroids. They are planet-sized worlds in their own right. Ganymede is the largest moon in the entire solar system, larger even than the planet Mercury. 3.8 billion years ago, these 4 Galilean moons were newly formed and were still settling into their modern state. Their composition, like that of the planets, was determined by their distance from the hot, glowing young Jupiter. Io, the innermost of the 4, formed in the warmest part of the Jovian subnebula. It is a dense, rocky world, composed primarily of silicate rock and an iron core, with very little water ice. Even in this early era, it was being subjected to the immense and competing gravitational pulls of Jupiter on one side and the other large moons on the other. This constant tidal flexing was kneading the moon's interior, generating a tremendous amount of heat. This heat made Io the most volcanically active body in the solar system, a title it still holds today. Its surface was a violent landscape of sulfurous volcanoes, constantly repaving itself with colorful lava flows. Europa and Ganymede formed farther out, where it was cold enough for water ice to be a primary building block. These are worlds made of a mixture of rock and ice. They differentiated into rocky cores surrounded by thick mantles of water. The same tidal heating that drove Io's volcanoes was also at work on these moons, though to a lesser extent. This internal heat was likely enough to maintain a liquid water ocean beneath their solid, icy crusts. These were the first great ocean worlds of the outer solar system, their hidden seas protected from the vacuum of space by a shell of ice. Callisto, the outermost of the 4, formed in the coldest, most placid region of the disk. It is a world of rock and ice that never fully differentiated. It has a mixed interior and was not subject to the same intense tidal heating. Its surface was, and still is, an ancient, dark, icy landscape, completely saturated with the craters from the late heavy bombardment. Callisto, much like our own Moon and Mercury, is a quiet museum of the solar system's violent youth. This diverse family of worlds, from a fiery volcanic planet to hidden ocean worlds to an ancient cratered ice ball, truly makes the Jovian system a solar system in miniature, a perfect laboratory for studying the processes of planetary formation and evolution. As the great storm of the late heavy bombardment began to fade, and the solar system began its long, quiet adulthood, Jupiter's role transitioned from one of chaotic architect to one of steadfast stabilizer. Having cleared the system of the majority of its dangerous debris, and having shepherded the other planets into their final orbital configurations, Jupiter's immense and steady gravity became the cornerstone of the solar system's long-term peace. The same resonances that once wrought havoc in the asteroid belt now serve to maintain its structure, keeping the majority of asteroids confined to stable orbits between Mars and Jupiter, and preventing them from straying into the inner solar system. Jupiter's gravitational influence acts as a great wall, protecting the terrestrial planets from the vast reservoir of comets in the outer solar system, the Oort cloud. It ensures that the orbits of the inner planets remain stable and predictable over billions of years, preventing the kind of chaotic interactions that could lead to collisions or ejections. Our solar system is a remarkably stable and orderly place compared to many of the exoplanetary systems we have discovered. We see systems with hot Jupiters, orbiting incredibly close to their stars, and systems with giant planets on highly eccentric, elliptical orbits that would have long ago disrupted any smaller, Earth-like worlds. The stable, nearly circular orbits of our own solar system, particularly in the inner regions, are a direct consequence of Jupiter's presence and its history. The Grand Tack hypothesis suggests that Jupiter may have migrated inward early in its history, perhaps as far as the modern orbit of Mars, before being pulled back out by the gravitational influence of Saturn. This inward and outward journey would have cleared out the original population of rocky bodies in the inner solar system, and then set the stage for the formation of the smaller, drier terrestrial planets we see today. In this sense, Jupiter is responsible not only for our solar system's stability but for its very composition. And so, as we take our leave of this colossal, swirling world and its family of diverse moons, we see it not just as a planet, but as the great anchor of our cosmic home. It was the agent of the final, violent storm of creation, and then it became the guardian of the long, quiet peace that followed. Its steady, powerful presence brought order to the chaos, creating the stable conditions that would ultimately allow the intricate story of life to unfold on a small blue world in its shadow. Drifting farther out into the cold and deepening twilight of the solar system, we approach the sixth planet, the serene and golden world of Saturn. While it is a gas giant like its larger sibling Jupiter, Saturn has a character all its own, defined by a lower density, a more subtle beauty, and of course its magnificent and iconic rings. 3.8 billion years ago, this jewel of the solar system was just beginning to acquire its most famous feature. From a distance, the young Saturn is a world of pale, subtle beauty. It is a gas giant, composed primarily of hydrogen and helium, but it is significantly less massive and less dense than Jupiter. In fact, Saturn's average density is less than that of water. If there were a bathtub large enough, Saturn would float. Like Jupiter, it rotates with incredible speed, completing a day in just over 10.5 hours, which flattens its shape, making it visibly wider at the equator than at the poles. And like Jupiter, the young Saturn was still radiating more heat from its interior than it received from the far-distant sun. This internal heat drove its weather, creating a system of atmospheric belts and zones similar to Jupiter's, but the view is much more muted and hazy. Saturn's colder temperatures allow for a thicker haze layer of ammonia ice to form in its upper atmosphere, which veils the more colorful and turbulent cloud decks below. The result is a world of gentle pastel colors, pale golds, soft yellows and creamy whites, a much calmer and more serene-looking atmosphere than the dramatic high-contrast storms of Jupiter. Saturn's position in the solar system is a crucial part of its story. Orbiting nearly twice as far from the Sun as Jupiter, it is a world of profound cold. Its gravitational influence, while still immense, is secondary to Jupiter's. It played a vital supporting role in the Great Planetary Migration, its gravitational dance with Jupiter being the very thing that triggered the system-wide instability. But it was always the junior partner, the second in command in the realm of the giants. The young Saturn was a world of quiet majesty, a golden globe hanging in the deep darkness. It had its own powerful weather, its own internal heat source, and its own growing family of moons. But its destiny and its identity would be defined by a feature that was just now beginning to form around its equator, a structure of such delicate and complex beauty that it would one day become the most recognizable and beloved silhouette in the entire solar system. The most captivating feature of Saturn is, without a doubt, its breathtaking system of rings. And while their exact age is still a topic of gentle scientific debate, one leading theory suggests that they are a relatively young feature, and that 3.8 billion years ago, they may have been in the very process of being born. The story of the rings is likely not one of peaceful, gradual accretion, but of sudden, catastrophic destruction. The theory begins with a large, icy moon. In the early, chaotic days of the solar system, Saturn, like the other giant planets, was surrounded by a large family of moons that had formed from its own subnebula. Let's call this lost moon Chrysalis. Chrysalis would have been a substantial world, perhaps the size of Saturn's modern moon Mimas or Iapetus, composed of a mixture of rock and a great deal of water ice. For hundreds of millions of years, it orbited Saturn peacefully. However, the orbits of moons are not fixed forever. Through complex tidal interactions with the planet and gravitational resonances with other moons, their orbits can slowly change over time. The theory posits that the orbit of Chrysalis became unstable. It was perhaps pushed by the gravitational nudges of the larger moon Titan, and it began a slow, inexorable spiral inward toward the giant planet. As Chrysalis drew closer and closer to Saturn, it approached a critical boundary known as the Roche limit. The Roche limit is the distance from a planet within which the planet's tidal forces the difference in the gravitational pull on the near side and the far side of the parabolit. Moon are stronger than the moon's own gravity that is holding it together. Once Chrysalis crossed this invisible line, it was doomed. Saturn's immense gravity began to stretch the icy moon, pulling it into an elongated shape. Fractures would have appeared all over its surface as the tidal stress grew. Finally, in a moment of silent, graceful, and catastrophic destruction, the moon was torn completely apart. It did not explode, but was simply and quietly shredded into billions and billions of pieces. The rocky core of the Moon would have largely plunged into Saturn's atmosphere, but the vast, icy mantle was dispersed into a flat, orbiting disk of debris around the planet's equator. This newly formed disk was composed of countless fragments of pristine water ice, ranging in size from tiny dust grains to chunks as large as mountains. Over time, the constant, gentle collisions among these ice particles would have caused the disk to spread out and flatten into the incredibly thin, vast structure we see today. The individual particles would have settled into orderly, circular orbits, creating the beautiful, shimmering ring system. So, as we gaze upon the young Saturn, we may be witnessing this very process. The rings are perhaps not yet the solid, bright structures we know, but a more diffuse, clumpy cloud of freshly shattered ice, the glittering, ethereal ghost of a lost moon, just beginning its long, slow transformation into the most beautiful and iconic feature in our solar system. Beyond the nascent rings, Saturn was surrounded by its own diverse and fascinating family of moons. Like Jupiter, Saturn had its own subnebula from which its major moons formed. But because Saturn is less massive and formed in a colder region of the solar system, its moons have a different character. They are, with one major exception, worlds of rock and primarily ice. 3.8 billion years ago, these icy moons were newly formed, and their surfaces were being intensely battered by the final stages of the late heavy bombardment. Worlds like Mimas, Enceladus, Tethys, Dione, and Rhea were accumulating the craters that still dominate their surfaces today. Their interiors were likely differentiated into rocky cores and thick icy mantles. The decay of radioactive elements and tidal heating from Saturn may have been enough to create and maintain liquid water oceans deep beneath the icy shells of some of these Illua-3s and oceans, not well-developed oceans. Moons, particularly Enceladus and Dione. These were small, cold, and distant cousins of the ocean worlds of the Jupiter system. But one moon in the Saturn system stands apart from all the others. Titan. Titan is a colossal moon, larger than the planet Mercury, and it is unique in the solar system for possessing a thick, dense atmosphere. Even in this early era, Titan was already wrapped in its thick, orange-colored atmospheric blanket. The atmosphere is composed primarily of nitrogen, like Earth's, but it is also rich in methane and other hydrocarbons. This thick, hazy atmosphere completely obscures the surface from view. The surface of the young Titan would have been an incredibly cold but fascinating place. The thick atmosphere would create a significant greenhouse effect, but because of the immense distance from the sun, the surface would still be frigid, far too cold for liquid water. However, it was possible that the temperatures were just right for liquid methane. 3.8 billion years ago, Titan may have had a methane cycle analogous to Earth's water cycle, with methane clouds, methane rain, and rivers and lakes of liquid methane and ethane on its surface. It was a strange, inverted version of Earth, a world where the role of rock was played by water ice, and the role of water was played by liquid hydrocarbons. The Saturn system, then, was a realm of ice, from the glittering, newly born ice rings to the battered, cratered surfaces of its mid-sized ice moons, to the strange, hydrocarbon-rich surface of the giant, hazy Titan. It was a diverse collection of worlds shaped by the profound cold of the outer solar system. It was a quieter, more subtle, and in many ways more mysterious system than that of its larger neighbor, Jupiter. As we conclude our visit to the Saturn system, it is worth reflecting on its calmer, more reserved character in comparison to Jupiter. While both are gas giants, the differences in their mass and location led to them playing very different roles in the solar system's story. Jupiter was the great disruptor and protector, the dominant gravitational force that dictated the architecture of the entire system. Saturn's influence was more subtle, but no less important. Saturn's primary role in the grand narrative was as Jupiter's partner in the dance that triggered the Great Migration and the late heavy bombardment. It was the gravitational relationship between these two giants, their slow approach to a perfect orbital resonance, that provided the necessary trigger for the system-wide instability. Without Saturn, Jupiter's orbit might never have been altered, and the final dramatic chapter of planetary formation may never have happened. Saturn was the catalyst, the quiet partner whose presence made the whole dramatic sequence of events possible. Beyond this pivotal role, Saturn's influence was one of a more gentle secondary shepherd. Its gravity helped to shape the outer edges of the asteroid belt and to influence the orbits of the countless small icy bodies in the region beyond it. But its reach was not as powerful or as all-encompassing as Jupiter's. It was a quieter, more distant giant, presiding over its own magnificent realm of rings and icy moons. This calmer nature is reflected in the planet itself. Its hazy, muted atmosphere lacks the violent, continent-sized storms that perpetually rage on Jupiter. Its family of moons, while diverse, is a more orderly and less extreme system than the Jovian worlds, which range from a fiery volcano to vast ocean worlds. Saturn is a world of serene and subtle beauty, a place of quiet majesty rather than overt power. As we drift away from this golden world with its nascent, glittering rings, we carry with us an impression of peace and elegance. It is the solar system's great jewel, a world whose story is one of quiet partnership, catastrophic creation, and the slow, patient formation of the most beautiful and iconic structure in our cosmic neighborhood. Our journey now takes us into the truly deep, dark, and cold outer reaches of the solar system. The sun is now a distant, star-like point, its warmth almost completely gone. Here, in the profound twilight, we find the two outermost planets, the enigmatic ice giants Uranus and Neptune. These are worlds of a different class entirely, and their story is one of a great ancient journey that reshaped the entire solar system. As we approach Uranus and Neptune, we see that they are fundamentally different from the gas giants we have just left. While they are still massive planets with thick atmospheres of hydrogen and helium, they are significantly smaller than Jupiter and Saturn. More importantly, a much larger fraction of their mass is made up of heavier materials, which planetary scientists refer to as ices. These are not just water ice, but also methane and ammonia, compounds that were solid in the cold outer regions of the protoplanetary disk. The internal structure of an ice giant is thought to consist of a small, rocky core surrounded by a vast, deep, and slushy mantle of these compressed, superheated ices. This icy mantle is not solid, but a strange, dense fluid. Above this is the deep atmosphere of hydrogen and helium, which is laced with a significant amount of methane gas. It is this methane that gives the ice giants their beautiful, distinctive colors. Methane gas is very good at absorbing red light from the sun, while reflecting the blue and green light. This is why Neptune has a stunning, deep azure blue color, and Uranus a paler cyan or aquamarine hue. 3.8 billion years ago, these two beautiful colored globes were worlds in motion, but not just in their orbits around the sun. They were nearing the end of a long, slow journey that had taken them far from where they were born. The leading theory of our solar system's formation, known as the Haze model, suggests that all of the giant planets formed in a much more compact configuration, much closer to the sun. Uranus and Neptune were likely born in the region between the primordial orbits of Jupiter and Saturn. They did not stay there. Through gravitational interactions with each other, and with the vast disk of planetesimals that lay beyond them, Uranus and Neptune began to slowly migrate outward. This was a journey that took hundreds of millions of years, a slow, graceful spiral into the cold, dark outer solar system. It was this very journey, this great migration, that was the ultimate cause of the late heavy bombardment, as the gravity of the outward-moving ice giants ploughed into the primordial Kuiper belt, scattering its icy bodies in all directions. As we arrive in this distant realm, Uranus and Neptune are just settling into their final modern-day orbits, their long journey at last coming to a peaceful end. Let us now delve more deeply into this grand and transformative journey of the ice giants, for it is one of the most important events in the story of our solar system. The concept of planetary migration, as described by the Haze model, has revolutionized our understanding of how our planetary system came to be. The story begins with the four giant planets Jupiter, Saturn, Uranus, and Neptune forming in a much tighter, more compact configuration, perhaps all within about 15 astronomical units of the Sun, which is inside the modern orbit of Uranus. Beyond them lay a massive, dense disk of icy planetesimals, the leftovers from the formation of the outer planets, containing perhaps 30 Earth masses of material. This vast disk of small bodies was the fuel for the migration. The giant planets began to interact gravitationally with the inner edge of this disk. Occasionally, a planetesimal would stray too close to one of the ice giants, like Neptune. Neptune's gravity would then fling the planetesimal inward, toward the other giant planets. Due to the law of conservation of angular momentum, every time Neptune threw a small body inward, it would itself be nudged slightly outward. It was a slow, patient exchange of energy. The inwardly flung planetesimal would then encounter Uranus, which would also give it a gravitational kick, sending it farther inward, while Uranus in turn was nudged slightly outward. This process would continue with Saturn, and finally with the great Jupiter. Jupiter, being the most massive, would typically have the final say, usually ejecting the small body from the solar system altogether. This cascade of gravitational encounters created a slow, steady outward migration for Saturn, Uranus, and Neptune, as they were constantly flinging material inward for Jupiter to clear away. Jupiter, in turn, moved slightly inward as it ejected the material from the system. This process unfolded peacefully for hundreds of millions of years, the outer planets all drifting in unison, slowly expanding their orbits. The process reached a dramatic climax when the two most massive planets, Jupiter and Saturn, crossed their powerful 2:1 mean motion resonance. This event destabilized the entire system. The orbits of Uranus and Neptune suddenly became more eccentric and chaotic. They were thrown much farther out and plunged deep into the dense planetesimal disk. This is what triggered the intense, sudden phase of the late heavy bombardment. The ice giants scattered the vast majority of the icy disk in all directions, sending a veritable blizzard of comets into the inner solar system and clearing out the outer regions. By 3.8 billion years ago, this chaotic phase is over. Uranus and Neptune have reached their new, distant orbits. The vast planetesimal disk has been depleted, with most of its mass ejected from the solar system. The great migration is complete. The ice giants, the two great wanderers, have finally arrived at their cold, lonely homes in the deep outer darkness, leaving behind a solar system that their journey has irrevocably and beautifully reshaped. As we focus our attention on Uranus, the seventh planet, we notice something profoundly strange about it. All the other planets in the solar system spin on an axis that is more or less upright relative to their orbit around the Sun. Earth's tilt of 23.5 degrees gives us our seasons. Jupiter is tilted by only 3 degrees, but Uranus is tilted on its side by an incredible 98 degrees. It essentially rolls along its orbital path like a ball, with one of its poles pointed toward the Sun for half of its long 84-year orbit, and the other pole for the other half. How did this happen? Such an extreme tilt cannot be explained by gentle, gradual processes. The most widely accepted theory is that early in its history, during the chaotic era of planetary formation and migration, Uranus was the victim of a colossal impact. It likely collided with another large protoplanet, perhaps a world the size of the Earth. This was not a head-on collision, but a grazing blow that was powerful enough to deliver a titanic gravitational shock and literally knock the planet over onto its side. This giant impact would have been a truly cataclysmic event. The energy of the collision would have been dispersed throughout the young ice giant, and the debris from the impactor and from Uranus itself would have been thrown into orbit around the planet. This orbiting debris cloud would have eventually coalesced to form Uranus's system of small icy moons and its faint dark ring system. This theory elegantly explains why Uranus's moons and rings all orbit around its equator, in the same plane as its extreme tilt. They were all born from the same single violent event that reoriented the planet. 3.8 billion years ago, Uranus was still reeling from this ancient catastrophe. It had settled into its new sideways rotation, and its family of moons had largely finished forming from the debris disk. Because of its bizarre orientation, the seasons on Uranus are the most extreme in the solar system. For 21 years, one pole experiences continuous direct sunlight, while the other is plunged into a decades-long dark and frigid winter. Then, during the equinoxes, the entire planet experiences a more normal day-night cycle as the Sun strikes the equator directly. This extreme tilt and the strange seasonal patterns it creates have a profound effect on the planet's atmosphere, leading to complex and dynamic weather patterns that we are only just beginning to understand. Uranus is the great oddball of the solar system, a world with a quiet, pale blue-green beauty that belies a violent and dramatic past. Its sideways tilt is a permanent scar, a silent testament to the incredible chaos and the planet-shattering collisions that characterize the solar system's youth. We now journey to the final planetary outpost of our solar system, the eighth and most distant planet, Neptune. Glowing with a deep, rich, azure blue color, Neptune is the last of the giants. It is slightly smaller but more massive and denser than Uranus, and it possesses the most violent and fastest winds in the entire solar system, with storms raging at speeds of over 2,000 kilometers per hour. Neptune's story, like that of Uranus, is defined by its outward migration. As it journeyed to its final position at the edge of the planetary system, its gravity became the dominant force shaping the region beyond, the realm we now call the Kuiper Belt. It shepherded the small, icy bodies of this region, locking many of them into stable orbital resonances with itself. Pluto, for example, is in a stable 3-2 resonance with Neptune, meaning it completes 2 orbits for every 3 that Neptune makes. This resonance protects Pluto from ever getting too close to the giant planet. Neptune is the great shepherd of this trans-Neptunian realm, the gravitational gatekeeper of the solar system's outermost frontier. But perhaps the most fascinating story of the young Neptune involves its largest moon, Triton. Triton is a unique and mysterious world. It is the only large moon in the solar system that orbits its planet in a retrograde direction, meaning it circles Neptune in the opposite direction to the planet's rotation. A retrograde orbit is a telltale sign that a moon did not form in place around its planet, but was instead a wandering object that was later captured by the planet's gravity. Triton was likely once a large dwarf planet, similar to Pluto or Eris, orbiting the Sun independently in the primordial Kuiper Belt. During the Great Migration, as Neptune was plowing through this region, the young Triton had a close encounter with the ice giant. It strayed too close and was caught by Neptune's powerful gravity, settling into its strange, backward orbit. The process of this capture would have been incredibly disruptive for any pre-existing system of moons that Neptune might have had. The newly arrived Triton, in its chaotic, eccentric orbit, would have swept through the Neptunian system, its gravity disrupting the paths of the smaller, regular moons, causing them to collide with each other or be ejected from the system. This is likely why Neptune today lacks a family of large, regular moons like those of the other giant planets. It traded its original family for this single, large, captured prize. 3.8 billion years ago, Triton was still settling in from this traumatic event. The tidal forces from Neptune were slowly circularizing its orbit, a process that would have generated enormous amounts of heat in Triton's interior, likely keeping it geologically active for 1 billion years or more. The story of Neptune and Triton is a final, beautiful example of the dynamic and chaotic nature of the young outer solar system, a story of a wandering giant capturing a wandering dwarf planet, a chance encounter in the cold, distant darkness that created one of the most unusual and compelling planetary partnerships in our solar system. As our visit to the ice giants draws to a close, we can look back on them as the great sculptors of the solar system's final frontier. Their long outward migration was the single most important event in shaping the architecture of the entire system, from the inner planets to the most distant icy bodies. They were the agents of the Great Storm, the final chaotic resettlement that put the finishing touches on our planetary home. Once they arrived in their final distant orbits, their role changed from one of disruption to one of order. They became the shepherds of the outer darkness, their gravitational influence bringing a new and lasting stability to the solar system's vast, cold perimeter. Uranus, in its lonely, tilted orbit, presides over its own quiet domain. Its influence is more localized, governing its family of small, icy moons and its faint, dark rings. It is a system born of catastrophe, now settled into a long and peaceful, if sideways, existence. Neptune, as the outermost planet, has the more profound and far-reaching role. Its gravity is the undisputed master of the Kuiper Belt, the vast ring of icy debris that lies beyond its orbit. It has organized this belt, creating the sharp inner edge and shepherding countless small worlds into stable, resonant orbits. It has created a structure and an order that would not exist without its presence. It is the final gravitational wall of the planetary system, the guardian of the threshold between the realm of the planets and the even vaster, more mysterious realm of the comets beyond. Together, these two beautiful colored worlds stand as silent, frozen sentinels in the deep twilight. They are the quiet rulers of the solar system's vast, cold backyard. Their ancient journey defined the modern solar system, and their steady, silent presence has maintained its peace ever since. As we drift away from them and head even farther out into the darkness, we carry with us an image of these two wandering giants, the beautiful, enigmatic and powerful shepherds of the solar system's final quiet frontier. Our journey has now taken us beyond the orbit of the last planet, into a realm of profound cold and darkness. We are entering the Kuiper Belt, a vast, donut-shaped ring of icy bodies that orbits the Sun in the outer reaches of the solar system. This is the source of many of the comets we see, and it is the home of dwarf planets like Pluto, 3.8 billion years ago. This region was the last, fading echo of the solar system's formation, a place still reeling from the great migration of the giants. The Kuiper Belt is the third and outermost region of our solar system, after the inner realm of the rocky planets and the middle realm of the giant planets. It is a vast, icy debris field, a cosmic junkyard of material that was left over after the formation of the outer planets. But to call it a junkyard is to do it a disservice. It is better to think of it as a pristine, frozen museum of the solar system's birth. The bodies in the Kuiper Belt are planetesimals, the same building blocks that formed the planets, but which were too sparse and too gravitationally stirred by Neptune to ever coalesce into a large world. They are composed of a mixture of rock, water, ice, and frozen volatile compounds like methane and ammonia. Because they have spent their entire existence in the deep freeze of the outer solar system, they are the most primitive, unaltered objects we can study. They are perfect time capsules, preserving the original chemistry of the solar nebula from 4.5 billion years ago. 3.8 billion years ago, the Kuiper Belt was a much more dynamic and populated place than it is today. Before the great migration of Uranus and Neptune, it was a much more massive and denser disk of material. But the outward journey of the ice giants had a profound and dramatic effect on this region. As Neptune ploughed into the primordial belt, it scattered the vast majority of its original inhabitants. Most were ejected from the solar system entirely, flung into interstellar space. A smaller fraction were sent hurtling into the inner solar system, becoming the cometary component of the late heavy bombardment. The Kuiper Belt we see today is the faint, depleted remnant of this once mighty disk, containing perhaps only 0.1% of its original mass. The bodies that remain are the survivors, the ones that were lucky enough to be nudged into stable, long-term orbits, often under the gravitational protection of Neptune. The Kuiper Belt of 3.8 billion years ago was a region in the final stages of this great clearing out. The storm was fading, but the space here was still filled with the echoes of that ancient disruption. It was a realm of 1,000, or rather, 1 billion small, icy worlds, just beginning to settle into the quiet, frozen existence they would maintain for the next 4 billion years. Among the countless small, icy bodies of the Kuiper Belt, a few grew large enough to be considered worlds in their own right. These are the dwarf planets, objects massive enough for their own gravity to have pulled them into a round or nearly round shape. The most famous of these is Pluto, but we now know of several others, including Eris, Makemake, and Haumea. 3.8 billion years ago, these were the young kings of the Kuiper Belt, the largest objects to have formed in this distant realm. They were born from the same process of slow, gentle accretion as the other planets, but in a region where the building materials were too spread out to form a truly giant world. These dwarf planets are not just inert balls of ice and rock. They are complex geological worlds. In their youth, the heat from their accretion and from the decay of radioactive elements in their rocky cores would have been enough to cause them to differentiate. They likely developed rocky cores surrounded by thick mantles of water ice. For many of them, This internal heat may have been sufficient to maintain a layer of liquid water deep beneath the surface, a hidden subsurface ocean. The young Pluto, for example, may have been an ocean world, its vast, dark sea protected from the cold of space by a thick, insulating shell of ice. The surfaces of these dwarf planets would have been a canvas of complex geology. The slow freezing of their subsurface oceans would have caused the water to expand, creating enormous cracks and faults in the icy crust. Cryovolcanism may have been common, a process where slushy, icy lavas of water, ammonia, or methane erupt from the interior and flow across the surface, creating smooth plains and strange mountainous features. We see evidence of this ancient activity on the surfaces of Pluto and its large moon Charon today, and of course their surfaces would have been heavily cratered by the impacts of their smaller neighbors in the Kuiper Belt. This was a chaotic environment, and collisions were common. The strange, fast-spinning, elongated shape of the dwarf planet Haumea and its family of small, icy moons are thought to be the result of a massive collision with another large Kuiper Belt object early in its history. The dwarf planets are the fascinating, complex and dynamic rulers of this distant, icy kingdom, each with its own unique story of formation, geological activity, and survival in the cold, dark frontier of the solar system. The Kuiper Belt is not just a static museum of ancient worlds. It is also an active reservoir, the source of a specific class of comets that still visit the inner solar system today. These are the short-period comets, those with orbits of less than 200 years. They are the beautiful, icy visitors whose predictable returns have been recorded by astronomers for centuries, and their journey begins here, in the distant realm sculpted by the gravity of Neptune. The Kuiper Belt objects are in stable orbits, but they are not perfectly stable forever. The occasional gentle gravitational nudge from the giant planets, particularly Neptune, can disturb the orbit of one of these small, icy bodies. This slight perturbation can be just enough to push the object onto a new, more elliptical path, one that takes it out of the Kuiper Belt and sends it on a long, slow fall toward the Sun. Once its orbit is changed, the object begins its long journey inward. It will cross the orbit of Uranus, then Saturn, and then the great Jupiter. Each of these giant planets will give it a gravitational kick, further altering its orbit. Many are ejected from the solar system at this stage, but some will survive this gravitational pinball machine and continue into the inner solar system. As this icy body from the deep freeze of the outer solar system approaches the Sun, it begins to warm up. The ices on its surface, water, methane, carbon dioxide, begin to sublimate, turning directly from a solid into a gas. This outgassing creates a glowing, temporary atmosphere around the object, which we call the coma. The pressure of the sunlight and the solar wind then pushes this gas and the dust mixed with it away from the comet, forming the two distinct, beautiful tails, a bright, curved dust tail and a fainter stration tail. A small, inert, icy world from the Kuiper Belt has transformed into a spectacular, active comet, a celestial messenger from the solar system's most distant and primitive realm. 3.8 billion years ago, at the end of the late heavy bombardment, this process was happening far more frequently than it does today. The Kuiper Belt was still settling after its great disruption, and Neptune was still nudging a large number of its inhabitants onto these inward, sunward paths. The sky of the inner solar system was still filled with the faint, ethereal tails of these visitors, the last, beautiful remnants of the great cometary storm. As our exploration of the Kuiper Belt comes to an end, we are witnessing the final, quiet moments of the solar system's most transformative era. The great migration of the giant planets, the journey that reshaped the entire system, is now complete. Uranus and Neptune have arrived at their final distant stations, and their orbits have become stable and nearly circular. Jupiter and Saturn have moved on from their powerful resonance, and have also settled into the calm, predictable paths they follow today. The music of the planets has shifted from a chaotic, dramatic symphony into a gentle, harmonious lullaby. With the planets now in their stable orbits, their gravitational influence on the remaining small bodies of the solar system also became more stable and predictable. Neptune, in its new, distant orbit, was no longer ploughing through a dense disk of material, but was now simply the gentle, distant shepherd of the depleted Kuiper Belt that remained. The intense, chaotic scattering of icy bodies that defined the late heavy bombardment came to an end. The asteroid belt, too, was settling down. The sweeping resonances that had cleared out so much of its population had passed, and the remaining asteroids were now in much more stable orbits, confined to their realm between Mars and Jupiter. The rain of rocky impactors on the inner planets slowed to a mere trickle. The entire solar system was breathing a collective cosmic sigh of relief. The era of formation, an epoch of unimaginable violence, constant collisions and wandering worlds, was finally truly over. The dust was settling, the orbits were fixed, and a new era of quiet, slow, and patient evolution was beginning. The planets, each bearing the unique scars and gifts of their chaotic youth, were now set upon their individual paths, free to evolve in the newfound peace and stability of a mature solar system. This moment, this quiet transition from a system in the making to a system in being, is the true dawn of the solar system we know today. Our journey through time and space has now brought us to a moment of profound and beautiful transition. The great storm has passed. The dust is settling. Across the entire solar system, from the scorched plains of Mercury to the frozen frontier of the Kuiper Belt, a deep and lasting quiet is descending. This is the moment the solar system grew up. Imagine the solar system as a vast celestial room where a great and energetic construction project has just been completed. For hundreds of millions of years, this room was filled with the dust, noise, and chaos of creation. Planets collided, worlds migrated, and debris flew in all directions. But now, the work is done. The celestial architects have packed up their tools and departed, and a deep silence is falling. The most visible sign of this newfound peace is the clearing of the space between the planets. The fine, primordial dust that had lingered from the solar nebula, the dust that created a faint, perpetual twilight throughout the system, has now been almost entirely swept away. It has been absorbed by the planets, ejected by the giant's gravity, or pushed to the outer fringes by the steady pressure of the sunlight and solar wind. For the first time, the space between the worlds is truly black, a deep and transparent void. The planets now shine as brilliant, sharp points of light against this dark backdrop, their individual character and color no longer muted by a cosmic haze. The rain of debris, the defining feature of the late heavy bombardment, has slowed to an occasional gentle sprinkle. The skies of the inner planets are no longer filled with the constant procession of comets or the brilliant flashes of major impacts. A celestial peace has been declared. This clearing of the skies was a crucial step in the evolution of worlds like Earth. The constant, sterilizing impacts were over, providing a stable and safe environment for the delicate, complex chemistry of life to begin its long and uninterrupted work. The planets themselves are beginning to find their equilibrium. The internal heat from their formation is slowly radiating away into space, and their surfaces are cooling and solidifying. The violent, globe-spanning magma oceans are giving way to stable, solid crusts. The period of most intense volcanism is beginning to wane. The solar system is transitioning from a state of high, chaotic energy to one of low, stable energy. It is like a great cosmic bell that has been struck, and we are now in the long, quiet moment after the ringing has subsided, listening to the final, fading hum. This is the new state of the solar system, a state of profound peace and stability that will last for the next 4 billion years. With this newfound quiet, the unique character of each planet, sculpted by the events of the preceding era, is now clearly defined. The stage is set for the next 4 billion years of planetary evolution, and each world is now on its own, distinct path. Closest to the Sun, Mercury stands as a silent monument to the great storm. Its surface, heavily cratered and wrinkled by its cooling, is a perfect, preserved record of the bombardment. Having endured the worst of the Sun's heat and the violence of the impacts, it now settles into a long, geologically quiet existence, a silent museum of the solar system's youth. Venus, the serene ocean world, is perhaps at the peak of its glory. Its thick clouds reflect the sunlight, and its greenhouse atmosphere maintains a gentle, warm climate. But the seeds of its future are already sown in its relentless volcanoes. which slowly add carbon dioxide to the air, a ticking clock that will one day transform this paradise into an inferno. Earth, our own home, is a dynamic and vibrant world. Its first oceans have formed, its first continents are beginning to take shape, and in the quiet, chemical-rich waters, the first tentative steps toward life are likely being taken. Its powerful magnetic field and active geology make it a resilient and ever-changing world, perfectly poised to begin its long and complex biological journey. Mars, the other blue planet, is on the cusp of a great sadness. Its golden age is ending. Its magnetic field is failing. Its atmosphere is beginning to thin, and its surface water is starting to freeze and retreat. The rivers will soon run dry, and the great northern ocean will become a frozen, dusty plain. Its story is a poignant reminder of how fragile a planetary paradise can be. Out in the cold, the giants have found their final homes. Jupiter, the great guardian, stands watch, its steady gravity now the primary force of stability in the system. Saturn's magnificent rings, born from the destruction of a moon, are now a shimmering, established feature. Uranus, the tilted giant, rolls along on its side, a permanent reminder of the chaotic violence of the past. And Neptune, the distant shepherd, patrols the system's edge, keeping the icy remnants of the Kuiper belt in their orderly frozen dance. The stage is set. The characters have all found their places. The great dramatic first act is over, and the long, slow and beautiful second act of planetary evolution is about to begin. As we reflect on this moment of cosmic quiet, we can see that the chaotic and violent era of the late heavy bombardment was not just an ending, but a profound and necessary beginning. It was a process that, while destructive, ultimately delivered the essential ingredients for the solar system's most interesting and complex future: the seeds of life. The Great Storm was a cosmic delivery service on an unimaginable scale. The comets, flung in from the Kuiper belt by the migrating ice giants, were the great water-bearers. They slammed into the dry, rocky inner planets, delivering the vast quantities of water ice that would condense to form the first oceans on Earth, and perhaps on Venus and Mars as well. The bombardment turned hot, barren rocks into blue, watery worlds. But the comets, along with the carbonaceous asteroids from the outer asteroid belt, brought more than just water. Locked within their ice and rock was a precious cargo of organic molecules. These are the carbon-based compounds, amino acids, nucleotides, and other complex structures that are the fundamental building blocks of life as we know it. These molecules were forged in the interstellar clouds that predated our solar system, and were then incorporated into the planetesimals that formed in the cold outer TESS regions. The Great Storm liberated this material from its frozen prison and delivered it, by the trillions of tons, to the warm, wet surfaces of the inner planets. The bombardment created the very environments where these seeds could take root. The impacts created vast basins that would hold the new oceans. The heat from the impacts drove hydrothermal activity, creating energy-rich chemical gradients on the seafloor. The storm delivered the water, the organic chemistry, and helped to create the perfect incubators for that chemistry to become biology. And so, as the solar system settled into its long peace, the stage was not just set for geological evolution but for biological evolution as well. On at least one world, our Earth, the seeds delivered by this ancient storm would find fertile ground. In the quiet, sunlit waters of the primordial oceans, a new and remarkable process was about to begin, a process that would eventually lead to consciousness and to a species that could look back in time and wonder about the very storm that had made its existence possible. The Great Bombardment was the final, violent and generous act of creation that prepared our solar system for its most profound and beautiful story. Our long journey back through 4 billion years of time is now nearing its end. We have witnessed the birth of the modern solar system, the final chaotic storm that shaped the planets, and the quiet peace that followed. Now, as we gently return to our own time, we can reflect on how we know this ancient story, and what it means to be a part of it. How can we possibly know what the solar system was like so long ago? We have no time machine to take us back. The story we have just explored has been pieced together through a beautiful and patient process of cosmic detective work, reading the faint clues and ancient scars that have been preserved for billions of years. The most important page in this history book is our own moon. Because it has no atmosphere and has been geologically quiet for eons, its surface is a perfect, unaltered record of the late heavy bombardment. When the Apollo astronauts brought back lunar rock samples, scientists were able to date them using radiometric techniques. They discovered something astonishing. A large number of the rocks that were melted by impacts all clustered around the same age, roughly 3.9 billion years ago. This suggested that the bombardment was not a long, slow decline from the beginning of the solar system, but a distinct, relatively brief spike in impacts. A true cataclysm or storm. By counting the craters in different regions of the moon and tying them to the absolute dates from the Apollo samples, we can create a timeline of the bombardment. We can then apply this timeline to other worlds. When we look at the battered, ancient surfaces of Mercury or the southern highlands of Mars, we see the same density and distribution of craters. We can therefore infer that they all experienced the same storm at the same time. These quiet, scarred surfaces are the eyewitnesses to the past. The meteorites that fall to Earth provide another crucial piece of the puzzle. These fragments of asteroids are pristine samples of the solar system's original building blocks. By studying their chemistry, we can understand the ingredients that were available to form the planets and the life upon them. And finally, we have the power of computer simulation. By inputting the laws of gravity and the likely starting conditions of the early solar system, scientists can create models that simulate how the planets would have interacted and evolved over billions of years. It was through these models that the beautiful idea of planetary migration, the NICE model, was born. These simulations showed that a migrating group of giant planets could perfectly explain the timing and intensity of the late heavy bombardment, as well as many other strange features of our solar system's architecture. It is a story told not by a single piece of evidence, but by the gentle and patient weaving together of rocks from the moon, fragments from the asteroid belt, images from distant worlds, and the elegant, predictive power of mathematics. This journey into the past reveals a profound and beautiful truth. All the worlds of our solar system are family. They were born from the same cloud of gas and dust. They were built from the same basic ingredients, and they all endured the same, shared, formative experience of the great cosmic storm. When we look up at the planets in our night sky, we are not looking at strangers, but at our distant cosmic siblings. Mercury, the resilient survivor, tells us of the violence that our own Earth must have endured, its scarred face a mirror of our own planet's lost youth. Venus, the lost paradise, is our twin, a poignant reminder of how a subtle difference in circumstance can lead to a profoundly different destiny. It teaches us about the delicate and fragile balance that allows a world to remain habitable. Mars, the fading water world, is a story of planetary loss, a world that once held so much promise but could not hold on to its warmth. Its dry riverbeds and dusty lakebeds are a call to our curiosity, a search for a second, independent genesis of life. The giant planets, our powerful and distant cousins, are the architects and guardians of our home. Jupiter's gravity shaped our world's formation and has protected it ever since. Saturn's rings are a monument to the chaotic destruction that was once commonplace. And the ice giants, Uranus and Neptune, are the great wanderers whose journey defined the final structure of our entire planetary family. And the smallest bodies, the asteroids and comets, are our direct ancestors. The very water in our bodies, the carbon in our cells, the iron in our blood, much of it was delivered to the Earth by these humble, icy and rocky messengers from the outer solar system. We are, in a very real and literal sense, made of stardust, assembled by comets. This shared beginning connects us to every world. The story of the solar system is not just the story of Earth. It is a single, vast, interconnected story. Understanding this shared heritage gives us a sense of place, a sense of belonging not just to our own world, but to a vast and beautiful system of worlds. It fosters a quiet sense of empathy for the other planets, for their own unique stories of fire, ice, chaos, and peace. They are not just objects of scientific study, but characters in our own grand cosmic family history. The moment of cosmic quiet that descended upon the solar system 3.8 billion years ago was not an ending. It was the closing of a single chaotic chapter. and the opening of a much longer, and in many ways, more interesting one. It was the beginning of the immense, unfolding journey of planetary evolution. For the next 4 billion years, each planet would follow its own solitary path. Mercury and the Moon would remain largely as they were, quiet and preserved. Venus would begin its slow, tragic descent into a runaway greenhouse inferno. Mars would lose its atmosphere and its water, transforming into a cold, red desert. The giant planets would continue their slow, majestic dance in the outer darkness, their storms raging and their moons orbiting in a state of long-term, stable peace. And on Earth, the most remarkable journey of all would begin. The seeds delivered by the great storm took root in the warm, primordial oceans. Simple chemistry became complex biology. Single-celled life emerged and began a slow, patient 4 billion-year journey of evolution. This life would fundamentally transform the planet, filling its atmosphere with oxygen, painting its continents with green, and eventually producing a species capable of consciousness, a species that could build telescopes and spacecraft and piece together the very story we have been sharing tonight. Our presence here, now, is the latest, and perhaps the most extraordinary, development in this long unfolding story. The journey of the solar system is not just something we study, it is something we are a part of. We are the inheritors of this ancient history. The stability created by Jupiter, the water delivered by the comets, the minerals forged in the heart of the Hadean Earth. All of these were necessary prerequisites for our own existence. And so, we are left with a sense of profound and peaceful wonder. Our calm, orderly solar system, the peaceful home we know today, was born from an unimaginable period of chaos and transformation. The journey from there to here has been long, patient, and beautiful. And the journey is not over. The planets continue to orbit, the sun continues to shine, and the great, quiet story of the cosmos continues to unfold, with us now, for the first time as its self-aware witnesses. Tonight, we have journeyed across an ocean of time, back to the dawn of our planetary home. We have seen that the serene and predictable solar system we know was forged in a crucible of wandering giants and a great cosmic storm. We have walked the shores of lost oceans on Venus and Mars, and witnessed the birth of Saturn's rings from the ghost of a shattered moon. This shared ancient history connects us to every world. The water in our oceans and the very carbon in our bodies are gifts from that chaotic past, delivered by icy comets from the dark frontier. We are not separate from this story. We are its continuation, a living memory of a storm that has long since passed. The narration is now coming to a gentle close. You have listened for a long time, and now, you have permission to let go. Allow my voice to fade into the background, along with any thoughts of planets or of time. There is nothing left to do but to embrace the quiet that awaits you. May your rest be as deep and as peaceful as the silent space between the stars. As you continue to drift, I invite you to wonder, what is your favorite celestial object to imagine when you gaze at the night sky? Thank you for allowing me to guide you on this journey tonight. Your quiet presence makes these explorations possible. If you found a measure of peace here, a like or a subscription is a gentle way of helping others find this calm as well. The universe is filled with endless stories, each waiting for a quiet moment to be told. Whenever you are ready for another peaceful voyage, our library of cosmic journeys is here for you. For now, however, simply rest.